Good morning. Buenos días. Is it working online? Well, good morning. Hello everyone here present and people in YouTube. Welcome to the MAST3RBoost project workshop about hydrogen storage opportunities for carbon materials. We are in INCAR, part of the CSIC in Oviedo, and first I want to thank Teresa for organizing the workshop and INCAR for hosting this workshop. We are very happy to be here. I think this is the perfect place for us to show MAST3RBoost project, the advances, and a general conversation on opportunities for carbon materials. We know we are a bit late already. We had some issues connecting to YouTube, so sorry about that. And we can start with the presentation and the welcome remarks. So, Fabián, the floor is yours.
Good morning, everyone. It's a great pleasure to welcome you all to the Rosa Menéndez Auditorium at the Institute of Carbon Science and Technology, INCAR. On behalf of our entire team, I would like to sincerely thank to the organizer for selecting INCAR as the venue for this important workshop. INCAR is a research institute of the Spanish National Research Council, located in Oviedo, in the north of Spain, in Asturias. Our mission is to advance both fundamental and applied knowledge in carbon science and technology. We are proud to have a multidisciplinary team working across several key areas, including the design of new technologies for decarbonizing industrial sectors, the development of advanced carbon materials for application in catalysis, environmental remediation, energy conversion and storage. One of our strategic research lines focuses on the development of high-performance carbon materials for any application. This includes advanced spore materials, hybrid materials, and nanostructured system designing to use in batteries, supercapacitors, hydrogen and hydrogen storage. We believe carbon materials offer unique opportunity in this field due to their tunable porosity, surface chemistry, and structural versatility. Hydrogen storage remains one of the key technological challenges in the transition to a sustainable energy system. Currently, commercially available methods include compressed hydrogen gas, typically used in mobile applications such as fuel cell vehicles, liquid hydrogen, which require cryogenic temperatures and is mainly used in aerospatial and industrial applications, and metal hydrides, which are more suitable for stationary application due to their high volumetric density and safety profiles. However, each of these methods presents a limitation in terms of cost, energy efficiency, and safety. This is where carbon-based materials can play a transformative role. Their lightweight structure, high surface area, and chemistry tunability make them promising candidates for next generation hydrogen storage systems. However, challenges such as designing an appropriate porosity, particularly ultramicro porosity, achieving high packing density in order to increase the amount of absorbent material introduced into the storage tank, and property engineering the storage system itself, including its exchanges, must be addressed in order to bring this technology to commercial level. We hope this workshop will serve as a platform to exchange ideas, foster collaboration, and inspire new approach that will have a look the full potential of carbon material in hydrogen storage technology. Thank you again for being here, and I wish you a productive and inspiring workshop.
Thank you very much, Fabián. It's a pleasure to have the INCAR director here opening this workshop, and thank you again for giving us the opportunity to be here. So, we are going to start with the workshop. We have 4 talks followed by a roundtable, And we'll have in the meantime 10 minutes pause between the third and the fourth talk. So let's start. Yes, thank you very much. Okay. So this first talk, the idea of this first talk is to give a bit of an overview of the state of the art of hydrogen storage, the different options, mostly focused on transport sustainability. And to begin with, the first question is why hydrogen matters for transport. Hydrogen matters because it's a clean energy. That's the most important part. If we can use hydrogen for transport, hydrogen-powered vehicles emit only water vapor, so zero emissions. It has other advantages: it's energy dense, quick refueling, and it's versatile. It could be used potentially for light-duty and heavy-duty vehicles. But there are challenges. As Fabián said, there are many challenges ahead of us before being able to use hydrogen in the market, in real technologies that are deployed. And the first problem comes from the low volumetric density of hydrogen. Hydrogen is very light, but it's bulky. Yes, so you have an idea, 1 kilogram of hydrogen can fit 11,300 liters, which is more or less the cargo space of that van. In order to be commercially available or commercially deployed, the general consensus is that a tank for a normal car must have 5 kilograms of hydrogen to have a driving range that it is acceptable for the market. So as you can imagine, we cannot have a tank that is the size of 5 vans in a car. So that's the biggest challenge. And for that, there are some possibilities. That is basically increase the density. There are 2 main ways of doing it, which is cryogenic conditions. This is lower temperature, make it in liquid, and obviously it's much more dense than when it's in gas at room temperature. Or the other option is to have high pressure tanks. We can go up to 700 or more bars. But both the cryogenic conditions and the high pressure tanks have some issues that are added to the deployment of these technologies. Mostly the cost. They are very expensive to make nowadays, and they are heavy. And as well, we need to think about the challenges of hydrogen is the safety concern. Flammability is an obvious one, but as well, the small molecule size is a problem. Hydrogen is very, very small. It's so small that it can seep through many metals, and it can leak through many, many places, which means that we need new materials that can have leak prevention, and we need to add monitoring to the systems. So this is a bit of a general roadmap for hydrogen storage in vehicles. There's been lots of research advancing what the possibilities are for having hydrogen-fueled vehicles. However, it seems nowadays pretty clear that for light vehicles, normal vehicles, it's difficult that the technology of hydrogen-fueled vehicles is going to be competitive versus electric vehicles. However, there's no one solution fits all for transport. And we believe that there is, for long range or for heavy duty, hydrogen could be a possibility, but more research needs to be done to get there. And this is the Department of Energy of the United States has set some goals in order to get this hydrogen storage technology based on the market expectation. In this table, I just want to focus a bit in volumetric capacity, is that the density. As I said before, the acceptable driving rate is 5 kilograms of hydrogen in the tank. And for that, what it is expected, and the numbers have been changing over the years, is 40 grams per hydrogen. Now is closer to 50 grams of hydrogen per liter of the system. And the cost of the system should be under 9 or 8 kilowatts hour. In this onboard technology, the front runner is compressed gas at 700 bars, but we are there. We are not yet there, so more research needs to be done. In case of heavy duty, we are a bit behind. We are expected to reach similar level of maturity within 5 or 10 years. For midterm 2030, it is expected that we will be able to have some low-cost vessels for high pressure for these heavy-duty challenges. And even further, long-term 2036 is when we expect to have innovative hydrogen storage material for high density and low pressure. For heavy duty, requires 50 to 500 kilograms of hydrogen per tank, and multiple units of storage has to be in each vehicle. However, the expected cost is the same as light duty, $9 per kilowatt. So a bit of a quick overview of the types of hydrogen storage that there are out there. There are different hydrogen storage strategies, and what we are going to focus on this talk is in the physical techniques: compression, liquefaction, and cryocompression. Compression technology at 700 bars has been developed over years from Type 1 to Type 5 different vessels. From Type 1 to Type 5, it goes from the heaviest to the lightest, but the price increases accordingly as well. Right now, Type 4 seems to be the choice for compressed gas technology at 700 bars for hydrogen mobility. The advantages of this compressed technology is that it's mature and commercially proven technology, works at room temperature, and it's a simple principle. We just have compressed gas. There are some disadvantages. The first one is that it's 700 bars, so it's a high pressure, and that increases the cost of the tanks. But there is another problem, and is the density. Even at 700 bars, the low volumetric densities are lower volumetric densities than other technologies. If you see this graph here, we are going to be seeing this in almost all the technologies where we are at room temperature and 700 bars. In terms of cost and performance, well, there are different documents. The cost is still too high. System cost is above $11, and the goal is 8 or 9. So it is a solution, but it's not perfect, and that's preventing widespread deployment. In heavy duty, there have been some advances, and there are some applications in the market, and some tanks that have been engineered specifically for heavy-duty vehicles. So definitely there's movement in this area. The second option is cryocompressed technology at 350 bars. There are two types of this technology depending on the ranges: liquefied hydrogen storage or cryocompressed. In case of liquefied hydrogen storage, the advantage is obviously is liquid hydrogen, so it's very dense, low pressure under 10 bars. Disadvantage is that you need to work at minus 253 degrees to have liquid hydrogen, and that consumes a lot of energy. Cryocompressed is a bit of in between, where there is some pressure, 350 bars, mid to high, and the temperature range is low, but doesn't have to be as low as with liquefied hydrogen. In this latest, the biggest advantage of this technology is that at low temperature, as you can see in the bar at 350, in the graph at 350 bar, you can get higher volumetric densities, which is very important for transport with hydrogen. The disadvantage is that requires cryogenic temperatures, so quite cold or very cold, and it still requires 350 bars pressure. And in terms of cost, in this prototype characteristics, it is still too high to be usable according to the American DOA, but it is cheaper, and it is expected to get cheaper over time, especially if you see here the differences. They are closer in the heavy duty, in this case buses, than light duty vehicles. And there are some market approaches. This is not really market, but at least they have, I think it was last year, they unveiled the first, world first cryo-compressed hydrogen heavy-duty truck. So movement in this area as well, trying to get to the market. And there is the third option, that is the one that we are going to talk more, and the MAST3RBoost project is involved, is the cryoabsorption technology. The working principle is that we have hydrogen stored, but it is absorbed on high surface area materials. The advantages of this technology is a lower operating pressure than the other technologies, 700, 350, and this is 100 bar, and less compression is required. The disadvantage is that we are still using very low temperature. Cryogenic conditions are always required, and therefore insulation of the tank makes it very expensive. This technology is relatively new and still under development. The way it works is that at low temperature we have some porous material where the very tiny hydrogen molecules can go into the micropores and be absorbed there. Once the hydrogen is absorbed, there's a temperature swing where we can discharge this hydrogen, and this is how it works inside of the tank. There have been some efforts in some, for instance, there are some US projects in order to get this technology from lab to a bit more of a scale up. They did 2-liter tanks that were tested with different configurations, and in both of them use MOFs as the absorbent material. And in 2022, and there was a call of Horizon Europe projects in order to advance more in storage of hydrogen. There were 2 projects that were MAST3RBoost and MOST-H2 that are working in the cryogenic absorption of hydrogen, and we'll have the project manager of MOST-H2 in the roundtable as well. And there were another couple of projects about chemical storage. So I'm gonna be talking a bit about our MAST3RBoost project. What are we doing in the project? And I'm going with the end. What do we want? This is spoiler alert. This is what we want to see at the end of the project. Is a demonstrator. We want to see what we are building is a new tank, completely designed for this project. That is of 22 liters. So you've seen the 2 tanks that I showed you before, they were 2 liters. So we are going much bigger than it was done before. And for that, we are creating new absorbent materials that in this case is activated carbon and MOFs that are being chosen, and I will explain the process that we have followed before to be tested in this demonstrator. And we will have this demonstrator working hopefully by the end of the year. How are we working in this project? Well, we have a consortium that is doing both parts, the ultraporous material and the vessel itself. For the ultraporous materials, the University of Nottingham, INCAR, CSIC, and 2 entities in South Africa, University of Pretoria and CSIR, we are developing the activated carbons and the MOFs. Once we finish the development of the small scale materials, we moved into the phase of scaling up, densification, and right now we have these 4 chosen materials ready to be tested. On the other part of the project, it was the development and the design of the new vessel. That was a group of engineers headed by Spike that they are designing and building this new vessel. And there's been some development in new materials with LKR and CDTech, where they try different materials for the materials and techniques for manufacturing this vessel. And we are now in the final part of the project. We have, if I'm not wrong, 8 months left. where what we are going to be working is in putting together the two sides of the project. Now that we have the absorbent materials ready and the manufacturing of the vessel is almost finished, we have the last steps when we have to actually use the prototype. So talking a bit about the porous material generation, we are using machine learning. The way that we are doing first with literature review and then with experimental data, we have put some inputs into the machine learning, like the experimental conditions used for the manufacturing of this small scale activity in carbons or MOFs, and we have put as well the results from those experiments, measuring be it the area, pore volume, pore size, or 1 bar or 100 bar hydrogen absorption. Scott will be talking later about problems that we have gathering data, because this is obviously the idea and it's very nice, but then you face real world problems. From this machine learning, we get some optimal experimental conditions in which the machine learning tells us what are the best activation conditions, what biomass we should use, the ratio of activating agent at biomass, temperature, heating rate, that we get some new products, that we measure the properties, and we feed back the machine learning. However, this is not perfect, and we don't get all these results at once. So it's been a bit challenging, and it was challenging during the project to use the machine learning, because sometimes you are missing some material properties, and it's been a bit difficult. In general, this is how we work. The machine learning gave us this material best conditions for the materials, and we got at the end some very good absorbent materials. We created activity carbons from agricultural residues, and we did by two methods: alkali activated carbons or CO2 activated carbon. And we got, this is the list of the best performing activating carbons with a hydrogen uptake at 100 bars. The best one is above 60 grams of hydrogen per liter. And we did some new MOFs as well. These are coming from urban residues using PET bottles and aluminum lined bricks. And here we have some data, in this case of pore size. And I chose to put here pore size just to give you an example of what happened during when we were trying to get to these materials. At some point during the project, we have these different materials created where we had some results. The most important, obviously, is hydrogen uptake at 100 bar. That's like the final goal. But we couldn't get all the hydrogen uptake at 100 bar of all the materials as quickly as we needed them. So we tried to get other predictors, measuring other conditions, and what we saw is that, for instance, in this case, when we plot together hydrogen uptake to average pore size, we thought, oh, average pore size is a good predictor, so we can use it. However, when you plot all the hydrogen uptake versus pore, what we saw is that it was not helping us as much. So machine learning helped us in that regards, and now we have these two in tens of kilograms activity carbon pellets and MOFs pellets and granulated MOFs that are going to go inside the demonstration vessel. The tank, we have built two tanks. After the design and simulations, geometry changed several times, and now we have two full tanks that are produced at 22 liter capacity. There are two, because we are going to use one to explode it, basically. We are going to see how much pressure it can hold, and the second one, and the one that hopefully is not going to explode, is the one that we are going to use for the final testing. So just milestones of the project, although you will be getting more details in the next two presentations. Using machine learning, we have synthesized 100 samples, 50 high activity carbon and 50 MOFs, some of them with really high hydrogen uptake. Of those 100, 4 have been selected, have been densified and made in the multi-kilogram scale. and 2 vessels have been designed and created. Right now they are doing through safety testing and will be ready for real usage application in the following months. So conclusions of where we are: hydrogen is strategic but not universal, probably better suited for heavy duty and long range because batteries are more effective for short range. Current storage is still a compromise. There's no perfect solution. 700 bars is proven technology but has some issues. Liquid hydrogen has the challenges of boil off, and there is possibilities for using cryosorbent technology. If we can combine this lower pressure with cryogenic density, we might be able to have a winner here for this heavy duty. However, we are still in a low TRL, so far for deployment, and more research needs to be done in adsorbent materials, MOFs, activity carbons, and integrating these materials, collaborating with not only material science, but system engineers and industry in order to move forward this technology and get to deployment. This is all the time. I don't know if I'm behind. Good. Okay. Perfect. So we will have time later on in the roundtable for questions and comments. So we are going to go now to the second talk. It's from Marta Sevilla. Marta Sevilla is a research scientist here at INCAR. She's a chemical engineer and holds a PhD from the University of Oviedo. And she's conducted research at the University of Nottingham, the Max Planck Institute of Colloids and Interfaces, and the Georgia Institute of Technology. Nowadays, she leads INCAR's Functional Porous Materials group, where she develops carbonaceous materials with controlled porosity, mainly for energy applications. So, make this.
Well, good morning, everybody. In this presentation, I'm going to summarize part of the results that I have achieved so far in this project in relation to the design of a carbon material for hydrogen storage. As Sergio has said, we are targeting the storage of hydrogen under cryogenic and high-pressure conditions, and under these conditions, it has been shown that the hydrogen storage capacity of porous materials is determined by the surface area and total pore volume, with micropores playing a leading role. Accordingly, a hydrogen storage material must be highly microporous with a surface area in excess of 500 square meters per gram, and it must be also and obviously stable under the operating conditions and during cycling. As we all know, carbon materials can meet these requirements, standing out for being lightweight, having good chemical, thermal and mechanical stabilities, also easy to tune textural and chemical properties, and potential cost effectiveness and sustainability. In particular, these last two aspects are very important for the widespread implementation of any technology, and they have been addressed in this project through the carbon precursor by using abundant and inexpensive biomass residues, such as, for example, pistachio shells, eucalyptus sodas, or date seeds, and also biomass-derived substances such as glucose, tannic acid, or agar-agar, among others, and also through the synthesis process by using conventional activation approaches, including potassium hydroxide chemical activation implemented at the University of Nottingham, which is the most exploited methodology when ultra-high surface area is seeked, and also a more environmentally friendly CO2 physical activation approach implemented here at INCAR and that I will describe in this presentation. So the CO2 activation process is a gas-solid reaction where we have two processes involved. On one hand, the chemical reaction between carbon and CO2, and on the other hand, the diffusion of CO2 along the carbon particles. If we want to achieve a uniform process distribution in the micropore range, We must precisely control these two processes, since, as can be seen in this figure, if the chemical reaction is much faster than diffusion kinetics, we will just burn off the surface of the particles without creating any porosity. If the chemical reaction is faster than diffusion, the reaction won't take place uniformly along the particles, so that we will produce a broad pore size distribution, which includes large pores, which are not efficient for hydrogen storage, and that will also decrease the packing density. And only when the chemical reaction is slower than diffusion, the reaction will take place in a uniform way along the carbon particle, leading to material with a uniform pore size distribution in the micropore range. To achieve this condition, we need a precise control over the temperature, which dictates the reaction kinetics, the particle size, which control diffusion kinetics, and also of the mineral matter, since certain metals, like the ones here indicated, can catalyze the gasification reaction, leading to the complete burn-off of the material without creating porosity. Taking these considerations into account, in this project we have selected certain sustainable carbon precursors. On one hand, biomass residues characterized by a low ash content, such as pistachio shells and eucalyptus sawdust, which have less than 0.2 and 0.9% of ashes. And on the other hand, polymer microspheres produced from sustainable monomers, such as fluoroglucinol and glyoxylic acid, instead of the most frequently used petroleum-derived resorcinol, phenol, and formaldehyde. In this case, we have no ash content and a small particle size, which, as I have just said, are two characteristics necessary to perform the CO2 activation under chemical control. So in this case, the synthesis of highly microporous carbons is quite straightforward, and as I will show, we only need to control the activation temperature. However, in the case of the biomass residues, we have mineral matter and also large particle size. So in order to produce a carbon precursor suitable or with suitable characteristics to perform the CO2 activation process, we explore different transformation approaches shown in this scheme by using pistachio shells as a starting point. These transformation approaches include an initial washing step with sulfuric acid, polymerization step also with sulfuric acid, and a hydrothermal carbonization process, and we compare all of them to the direct pyrolysis of pistachio shells. As revealed by the elemental chemical analysis, all these pretreatments lead to an increased fixed carbon content, which raise the yield of the carbonization process, reducing in this way the carbon footprint of the process. This is especially remarkable in the case of the polymerization step and the HTC process, which increased the global yield of the carbon synthesis process by more than 30% compared to the other two routes. Besides, in the case of the acid washing step and the HTC process, we could completely remove all the mineral matter from the biomass, but in the other two cases, there are still acids remaining even after a post-carbonization acid washing step with diluted hydrochloric acid. These acids, consisting of calcium and potassium, as examined through EDX and also X-ray fluorescence, which, as I will show, will negatively affect the CO2 activation process. In relation to how these pretreatments affect the particle morphology, SCM shows that in the case of both acid pretreatments, washing and polymerization, they lead to a more open structure than that of pistachio shells as a result of the hydrolysis or dissolution of the hemicellulose content of biomass, which leads to the reorganization of the rest of the components. And in the case of the HTC process, there's a complete transformation of the morphology of the particles, obtaining the typical microspherical particles of secondary hydrochar, which come from a hydrolysis and repolymerization process. So all of these pretreatments seem profitable for the generation of carbon materials with an open structure and accordingly better diffusion kinetics. So we studied the CO2 activation of these 5 carbons under similar conditions up to a similar burn-off degree of more or less 55 and also a similar activation temperature, though in the case of the carbons produced by direct pyrolysis polymerization by sulfuric acid, we had to decrease the temperature down to 820 degrees, since at higher temperatures we couldn't get any product because of the complete burn-off of the material. But in spite of using that lower temperature, the reactivity, which is expressed as the burn-off degree as a function of time, is much higher in these carbons, in the range of 5 to 10 compared to around 2 for the other carbons, which can be ascribed to the presence of the mineral matter in these carbons, calcium and potassium, which catalyze the reaction. If we compare now the textural properties, in the case of these two carbons, the textural properties are poorer with lower values of surface area and also a broader pore size distribution, which shows pores up to 5-6 nanometers, whereas in the case of the other three carbons, all the pores are below 2 nanometers. They are strictly microporous. This low efficiency in pore generation can be better seen in this graph, which represents the BET surface area against the burn-off degree, where it can be seen that these two carbons follow the same trend below the others, in which not all the carbon atoms give rise to porosity. So no matter how much we increase in this case the burn-off degree, that we are not going to be able to produce materials with the same values of surface area as in the other three carbons. So we focus now on these three free as activated carbons and explore increasing the burn-off degree in order to enhance the textural properties of the materials. As can be seen here, by increasing the burn-off degree above 70, we can produce materials with very large surface areas, above 2,700 square meters per gram, with more than 75% of the total pore volume corresponding to micropores. So they are still highly microporous. This can be more clearly seen in the corresponding pore size distributions here shown, where the micropore region is highlighted in blue. For burn-offs below 60, the materials only possess pores up to 2 nanometers, and when we increase the burn-off degree above 70%, the materials show pores also up to 2.6, 2.8 nanometers, with two maxima at around 0.9 and 1.7, 1.8 nanometers, and also a somehow minor contribution there at around 0.5 nanometers. So the materials are still highly microporous, but there's the typical widening that has been observed with increase of the burn-off degree during the CO2 activation of a variety of carbon precursors. And in fact, these pore size distributions are quite similar to those obtained with potassium hydroxide activated carbons with similar values of surface area. This lower efficiency, the fact that we are creating porosity in an efficient way can be also seen in this graph, where all the materials follow the same trend of increasing porosity with the burn-off degree. So both the initial pretreatment with sulfuric acid and the HTC process allow the production of highly microporous carbons as a result of the complete removal of the mineral matter. However, if we now take into account the yield of all the synthesis processes included involved in the synthesis of these materials, the pretreatment, the carbonization, and this activation step, it can be seen that to achieve the same value of surface area, the synthesis process that involves a hydrothermal carbonization process is the most efficient one. So we focus now on this HTC pretreatment. We selected it to try to optimize the synthesis of these highly microporous carbons. And thereby, as can be seen here, even though this low reactivity is beneficial for pore generation, this implies that we have to keep the reaction for very long times, which increases the carbon footprint of the process. Therefore, we studied increasing the activation temperature to increase the reactivity and shorten these reaction times. We prepare a variety of materials by increasing the activation temperature 10 degrees from 835 to 885 degrees, and for burn-offs between 60 and more or less 80%. And for the two hydrochars, though we mainly focus on the one synthesized at 230 degrees, since this low temperature has proven to be enough to produce highly microporous carbons, but here I only showing a few selected samples. As can be seen in the table, by raising the activation temperature, we can substantially increase the reactivity, which also shortens in a substantial way the reaction time by more than 50%, for example, at the highest temperature. But in spite of that, we are still working on the chemical control, as proved by the enhanced textural properties of the materials, which show values of surface area up to around 3,300 square meters per gram, and still microporosity is accounting for more than 60% of the porosity in these materials. Here we can see also how the process distributions are very similar independently of the activation temperature, and all these materials follow the same trend of increasing porosity with the etching of carbon atoms, that is, with the burn-off. And we further explore this strategy, which involves an HTC process with another abundant biomass residue, such as eucalyptus sodas, which has a higher ash content than pistachio shells, but still below 1%. When we subject this precursor to the HTC process, in this case, the macrostructure of lignin is preserved, as can be seen in these SEM pictures, being covered by the typical microspherical morphology of secondary hydrochar, which comes from the hemicellulose and acellulose components of biomass, and the degradation of lignin increases with temperature, as can be seen in these SEM thumbs. So in this case, the particle size is much larger. So we subjected the hydrochar materials to our milling step, which, as revealed by the SEM pictures, allowed to reduce the particle size below around 20 micron. In this case, the HTC process couldn't completely remove the mineral matter containing the biomass. However, it led already to a substantial reduction of about 40–60%. So we applied a post-carbonization washing step with diluted hydrochloric acid, which led to an additional reduction in the ash content. These acids consist of silicon and calcium in the case of the HTC material prepared at 230 degrees, but only silicon in the case of the HTC carbon prepared at a higher temperature, and that's why here the ash content didn't decrease much. If we now compare with the direct pyrolysis of sawdust, in this case, during the carbonization, the mineral matter concentrates up to close to 5%, with a slight reduction after the acid washing step. And in this case, besides calcium, we have also potassium, both of them catalyzing the reactions. So this impedes the CO2 activation of this directly pyrolyzed sawdust. Similarly to the pistachio shells, we studied the CO2 activation at different temperatures in the range of 835 degrees to 885 degrees, and for both the acid wash materials, which are indicated by the W, and the materials which were purified. Similarly to pistachio shells, well, their reactivity is around 2 for the lowest temperature, and it also increases with the rise of the activation temperature, leading also in this case to materials with very large surface areas approaching 3,100 square meters per gram, and again with more than 60% of the total pore volume corresponding to microporosity. And here we can also see the similar pore size distributions. If we now compare with the carbons that contain acids that haven't been subjected to the post-carbonization acid washing step, in the case of the, well, I forgot that in this case we can also substantially reduce the activation time by increasing the temperature. In the case of the carbon that comes from the HTC material prepared at 230 degrees, the reactivity increases for the same temperature, and the textural properties are poorer for a similar burn-off. However, in the case of the carbon that comes from the hydrochar, which only contains silicon, the reactivity is preserved, and textural properties are also similar for a similar burn-off. These differences in pore generation efficiency can be better seen again in this graph, where only the activated carbons that come from the carbons which contain calcium follow below the trend, showing a lower efficiency in pore generation. If we now compare with the activated carbons prepared from pistachio shells, we can see that all of them follow a similar behavior in pore generation efficiency. And the last precursor that we have studied is polymer microspheres, as I said at the beginning, produced from fluoroglucinol and glyoxylic acid. In this case, we have, as I also said, no wash content and a small uniform particle size, so we don't need any pretreatment, and just a direct carbonization, which induces certain contraction of the particles, which is typical of a carbonization process. But after CO2 activation, the particle size remains similar, which is a first indication that the gasification reaction is taking place inside the particles and not on the surface, with a consequent external particle consumption and decrease of particle size. And this is supported by the fact that in this case we can also produce highly microporous carbons, again with surface areas up to 3,300 square meters per gram, with more than 60% of microporosity, no matter which activation temperature we use. And we can also see here the similar process distributions to previous materials. And if we compare with the biomass residues, all of the precursors follow a similar behavior in pore efficiency, pore generation efficiency. And if we now take into account the yield of all the processes involved in the synthesis of the different materials from the different precursors, all of them follow also a similar behavior, so that all of them are good precursors for the production of highly microporous carbons by CO2 activation. And finally, we measure the hydrogen storage capacity at 77 Kelvin up to 100 bar, measurements which has been done at the University of Nottingham. And it can be seen that the materials with higher pore development are able to store around 9, close to 10%, which is the targeted performance in this project. And in accordance with literature data, there's a roughly positive linear correlation with both the surface area and the total pore volume, and also a positive correlation with the micropore volume, but only up to around 1 cubic centimeter per gram, which suggests that there is another underlying factor affecting the hydrogen storage capacity in these materials. And indeed, if we correlate for these materials the hydrogen uptake with the mesopore volume, we can see that there is also a roughly positive linear correlation, which indicates that the small mesopores can also positively contribute to hydrogen absorption at this pressure. Well, as I have just said, the materials with higher surface area can approach the targeted performance when total capacity is considered. However, in a full cell application, the system is going to work between 100 bar and a minimum pressure suitable for the fuel cell, which is 5 bar. So we must take into account the amount of hydrogen remaining adsorbed at such pressure. What does this imply? If we take as an example one of the highest surface areas materials, by doing the refueling and discharging at 77 Kelvin, the amount of hydrogen remaining adsorbed at 5 bar is as high as 4%, which decreases a lot the actual working capacity of these materials. However, by implementing, as in this project, a combined temperature and pressure swing adsorption system, which discharges at 170 Kelvin, we can reduce the amount of hydrogen adsorbed down to around 0.5%, so that the working capacity of these materials is quite similar to the total capacities here shown. And in relation to the volumetric performance, which is also very important for the considered onboard applications, the materials with the highest gravimetric uptake are also the ones showing highest volumetric performance, getting close, although below the 44 gram per liter targeted in this project, necessary to achieve the 33 grams per liter in the system, so that in these materials the high gravimetric uptake is able to compensate for the decreased packing density of such high surface area materials. I shall note that this packing density has been calculated based on the mild compaction of the powder material, but this is something that is being studied and optimized during upscaling, as I guess Sergio will talk about later. So overall, I've just seen that by the careful design of the synthesis process, it's possible to produce highly microporous carbons with a relatively narrow pore size distribution by CO2 activation, even of biomass residues and not just pure compounds. The implementation of an HTC process allows the removal of the mineral matter from biomass and also increases the global yield of the carbon synthesis process, which makes it highly attractive as a pretreatment of biomass, and the developed activated carbons store up to 9.8% of hydrogen and 33 grams per liter at the maximum pressure of 100 bar. And when a temperature and pressure absorption system is used, they are able to store around 9% of hydrogen and 35 grams per liter. Well, thank you.
Hello? No. Oh yeah. So working? Yes. So we are a bit ahead of time. I don't know if we have a very quick question for Marta. We can go ahead now. If there is more of a comment or discussion, we can leave it for the roundtable. No. Well. Thank you very much, Marta. We can discuss later in the roundtable. So the third talk of today's workshop is from Scott, who's a research fellow at the University of Nottingham. He's part of the MAST3RBoost project as well. He works in the measurement, interpretation, and theory of absorption on porous materials. Scott completed his PhD in 2022 at the University of Nottingham, supervised by Professor Robert Mokaya. And more recently, he has developed the theory and tools to predict temperature-dependent absorption behavior from a single absorption isotherm. Whenever you want, Scott.
Cool. Thank you. Does this have a pointer? Does it? And is this my presentation? Great. Get it in presentation mode. And if I... Which one? This one. Okay, cool. Thanks for that introduction, and thank you to INCAR for hosting this workshop. So I'm going to talk a bit about how we actually measure hydrogen storage, which is perhaps one of the most important results from this project, and also the most annoying thing to actually do, because the machines break all the time. So you can join in my pain for doing this. So first, we need to talk a little bit about what it means to store a gas. In this case, we're storing hydrogen, but we could be doing CO2, methane, or whatever. It's the same principles, essentially. And as Sergio and Marta have already talked about, we're basically using a porous material to increase the capacity of a tank. And that simply works by the gas filling the pores of the material. And this is a process that we call adsorption with a D, not absorption with a B. And this is illustrated quite nicely by this little guy here. So adsorption, you get the material on the surface, or the pie on the face, whereas absorption, you get the pie in the face, which would mean that the gas would go into the material, so like a gas absorbing with a B onto a liquid. But no, we're not talking about that. This time we're talking about pie on the face. So we have here a simple gas adsorption process. So we start here. This doesn't want to stay. We start here with the empty material, so the dry material with nothing adsorbed onto it. As you raise the pressure, the pore filling begins, so you get gas adsorbed onto single sites. And then gradually you form a monolayer, so a single layer of adsorbate of gas on the material. And then you start to form multi-layers, so layers on top of the first layer. And then eventually the pores will be completely filled. So now we understand what it means to store a gas. we need to talk a little bit. Is this still working? It is still on. Okay. I'm echoing less. So we need to talk about, when we're talking about storing a gas, we either think of it in per unit mass or per unit volume. So typically when we measure gas stored, we think per unit mass. So this is in units like moles per kilogram, gram per gram, weight percent, centimeters cubed per gram, everything per unit mass. We could even use this unit, which if you can figure out what that means, then I guess you win a prize. Obviously we're not using that one. So this will answer a question like how much gas can 1 kilogram of our sample store? But when we are filling a tank with a material first, it's actually more important to ask how much gas can 1 liter of this material store? Or if my tank is 4 liters and I fill it with the material, how much gas will be stored? So as a result, we need to know the density of the material in question. This gets a little bit technical because there's different kinds of density, as people probably know. I've listed about 5 different kinds of density that I could think of. The first 3 are ones that we will actually care about. And I'm not going to go through all of the differences between them because I don't think it's particularly interesting for this talk. But all that to say, not only do we need to measure the amount of gas stored, but we will also need to measure the density of the material in order to convert that to a usable value for application in our tank, which doesn't look like this. So then we need to move on to isotherms. Because isotherms are the typical way that we measure and represent gas storage. So an isotherm is defined as the quantity of gas absorbed as a function of pressure at constant temperature, hence iso, same, therm, temperature. So that's the most common way of measuring and reporting static absorption. I'm missing, the formatting's gone a little bit here. So we're missing some text, that's fine. So this is the most common way, an isotherm is the most common way of measuring or reporting static absorption. Static meaning that the system is sealed and it's there's no gas moving in or out of the system when you measure how much gas is being taken up. So before this kind of measurement, your sample has to be degassed. If you've done any kind of BET experiments, you'll be familiar with this. So that sample has to be degassed, which is basically heating it under vacuum to remove any gas stuck to the surface. And then you can start your experiment. So all your experiment consists of is taking your degassed sample, raising the pressure with your gas, in our case hydrogen, and then allowing the system to equilibrate, and then determining from that, after the system is equilibrated, determining how much gas the material actually took up. So then it becomes very important about how we understand when the system has equilibrated. So we can see here on this top graph that, there's this big spike here where we increase the pressure. And it drops off a little bit because we usually overshoot a little bit compared to what we want to get to. And at the same time as the pressure goes up, the loading goes up, but then it drops down gradually. And so we want to figure out when the loading is no longer dropping, when it's actually the whole system is at equilibrium. Again, there's various ways to do this with different systems, different calculations you can make. But suffices to say, you need to design your experiment such that you are getting your data at the end when this line is flat, and not here when the loading is still dropping. Then we need to think about there's different kinds of machines to measure this kind of data. You have volumetric equipment, which actually there is quite a lot of this kind of equipment in this institution actually, and you have gravimetric equipment. So the volumetric, I'll go through this first. It's not what we actually use for hydrogen storage, but I'll go through this first just because it's more common and people are more aware of it. But a volumetric adsorption apparatus will determine the loading on the material based on pressure differentials. So basically, you'll have your sample inside a container and a reference, and it will the system will calculate how much gas is absorbed by reference to an empty cell. It's a much less complex and cheaper technique. But the problem with it, one of the problems with it, is that the uncertainties accumulate at the more data points you have. Again, for lots of technical reasons with maths that I'm not going to show here. So this kind of setup is typically used for low pressure experiments, typically for what we call the BET experiments, so when you're trying to determine surface area, etc. An example of this equipment is a micromeridics 3-flex, which looks like that. And I think there are one or two here, or do you have, oh, no, you have ASAP. Yeah, you have ASAP, you don't have this one. Okay, we have those ones, you don't. And the other option is you can do it gravimetrically. So gravimetrically measuring absorption is basically measuring the amount absorbed based on the weight of the sample, which seems simpler, but it actually ends up being more complicated. The fundamental function of it is quite simple, because it basically works like a really big thermogravimetric analyzer. So just basically a balance with a reference and a sample. But you have to put all of that into a big sealed system. And you also have to, because you're measuring very, very small changes in mass, you end up with a very delicate instrument that's very complex. But if it works, then you have way less uncertainty in your measurement. And as a result, it ends up being the better kind of instrument for high pressure experiments like the hydrogen isotherms that we run over at the University of Nottingham. So an example of this, and one that we have at the University of Nottingham is this Haydn Zemus. It's not very clear just by looking at these two pictures that these things are vastly different in size. So this is the same height as me, or a little bit taller. This is about this big. So they're very, very different, and this obviously has these two different parts to it. Yeah, so I'll talk a little bit about about the problems with this equipment. But first, let's go through a little bit of a diagram. So the Zemus basically looks like this if you were to draw a diagram. I'm not including the big box on the right that you saw on the previous slide, not this thing. Just the main part. So I think it might be easier if I come over here. So you have here two long wires that go up to a balance. So this is called a magnetic suspension balance. The way that it works, the magnetic suspension balance works, is that you run a magnetic field through, like across this beam here, and you try to keep the beam flat. And so the amount of power that you're required to keep the beam flat is calibrated to the weight of the sample, which is a very strange way to do it, a very complex way to do a balance, in my opinion, but it's very precise. And then, so as I said, these wires, which are thinner than a human hair, then go down to the reference side and the sample side. So you have some sort of standard reference, and you have your sample basket with your sample in it. I don't know if I can. That doesn't stay there. Okay. There's a reference side and the sample side, and that's all sealed inside two big steel reactors. And then apart from that, you have gas inlets and gas outlets, and so that you can basically measure the amount, the weight of the sample as you add or remove gas. Just to illustrate a little bit how delicate this is, I said that the wires are thinner than a human hair, so there's some of the wires are thinner than a human hair. Some of the wires are so thin that I can't actually see them, which when you try to open the machine up and then repair everything makes it very, very difficult. And this is something that I have to do quite often. So yeah, so that's how the machine works. We have some accessories for the machine, which are mainly for temperature control. So we have a cryo furnace, which is a furnace that has a temperature range of 123 to 773 K. The hot part of the furnace is probably pretty clear how that works. The cooling part of the furnace, so when you go down to these cryogenic temperatures, works on the basis of pumping liquid nitrogen through the furnace with a heat exchanger to control the temperature all the way down to 123 K. So that's very useful. You can use a water bath, which is pretty simple. That goes from room temperature up to the boiling point of water. Or you can use a dewar, which is as hot or cold as your cryogen. So typically we use liquid nitrogen at 77 Kelvin. So just to give you some idea of the specifications, so this can measure mass at a precision of 0.1 micrograms, and the mass stability is about 1 microgram. So it's a very, very precise instrument. The press precision is about 0.02%, and we can get a vacuum down to 10 to the minus 6 millibar. So as I say, very nice piece of equipment when it works. So enough about me complaining about the ZEMUS. Let's go into some technical parts about adsorption isotherms. When we are talking about these high pressure isotherms, it becomes important what considerations we're making. So these three graphs are all the same isotherm. But obviously they're quite different, especially when you get to the high pressure points. This is because when you start getting to high pressure, you need to be considering the amount of space that your material takes up relative to the gas itself. Again, I'm not going to go through all the maths, but if you ever do these kinds of measurements, you need to be aware that there's these different ways of reporting adsorption isotherms. So a net isotherm, so this lowest one in blue, is just the raw data. There's no extra calculations made to the data. And when we talk about an excess isotherm, we make an adjustment for the space taken up by the material itself. So you need to be able to understand you need to have a number for the skeletal density or volume of the material. The total makes an adjustment for the pore volume of the sample. So all of these three have different applications, and different uses, and there is a huge amount of debate amongst people in my field as to which one is correct and which one we should use when, and we can get very shouty sometimes. There are some researchers, and I think actually a growing number of researchers, that actually say anything except excess and net are meaningless. I don't know. I'll let them debate it, and then they can tell me. Yeah, it is also not only that. Not only are people debating, which ones are useful and which ones are not. People are debating if the definitions of the things that we don't know if they're useful or not are even correct, and maybe we need to change them. So yeah, that's part of my world sometimes. Marta already talked a little bit about working capacity, but I have a slide here too. Might even be the same sample. But just to reiterate, in the MAST3RBoost project, we are using a temperature pressure swing adsorption system, which means that we are charging the system, so filling the system at 77 Kelvin and 100 bar, and then we're emptying or discharging the system at 157-ish Kelvin and 5 bar. So this allows us to get a lot more of the gas out. You can see the two isotherms here. So this blue one is the 77, it actually went to 78 Kelvin, but not near enough. And this orange one is the the higher temperature isotherm at 157 Kelvin. And you can see when you do this, then you actually get quite a lot of gas out. So this sample, which I think was one of the carbon microsphere samples, it had a capacity at 100 bar of 9.2 weight%. And at the discharge conditions, so at 5 bar and 157 Kelvin, it was only 0.6 weight%, which means we only have a very small amount of hydrogen left in the material when we discharge. So in order to do this, basically you need to measure two isotherms. So as I said before, we have different temperature control things, temperature control accessories. So for the 77 Kelvin isotherm, you just use your liquid nitrogen dewar. But then for the higher temperature isotherm, then you need to use this fancy cryo furnace that allows you to control the temperature all the way down to those kinds of temperatures. If you found this really exciting and this is something that you really want to read more about, then there's all of this stuff that you can try to read. If you want to read all of the debates about what is the correct way to report high pressure adsorption data, especially for hydrogen, then this top one is actually really, really good. You might be a little bit confused because I am too, and I've been in this field for a long time. But yeah, there's a few other things. Here, I had to put one of my own papers, of course, but the one that I would particularly look out for is this bottom one, which has just come out like a couple of days ago, especially if you want to get into the nitty-gritty of what is technically the best way to report and measure this kind of adsorption data. I think that's it. Thank you. Do I need to give you this? Oh, yeah.
All right, thank you very much, Scott.
Where do I go? I'll go here.
We have some time before the break. I don't know if there is any questions, short questions that we can answer before the roundtable. I have a short question.
Yeah.
When you are talking about this net, excess, and total, I mean, I'm not sure if I can ask you for your personal opinion, was the right one, but in the graph I've seen that some of them were going down when the pressure was going higher.
Yeah.
How can you explain that? I didn't understand that part.
So when we, for example, if you're reporting a net isotherm, and actually I can go back to the slide just because it might be useful to see. Yeah. So when we're talking about a net isotherm, so this loading, it's actually, okay, if we had an empty container with no sample in it, and we increase the pressure with hydrogen, then the amount of hydrogen in the container would go up, right? So all that the net is showing is how much more hydrogen you can store than with the material than without it. So we can see that there's basically a peak here, and in theory, so basically, it doesn't mean that there's less hydrogen stored than, so when it's going down, it doesn't mean there's less hydrogen storage than without the material, but it becomes less useful, basically. So actually, if you follow these graphs, I'll talk about net because it's the easiest one to think about, this will eventually go negative. So, and that basically indicates that using your material at that high pressure is actually not advantageous for storing hydrogen. You might as well have use an empty container with no material in it. Is that?
Yeah, makes sense. Yeah, thank you very much. Any other questions? Okay, so if we don't have questions here, we are gonna have this break now, and we will have 20 minutes break that we will be using to connect for the roundtable with the people that are not gonna be here. So we reconvene, and we will have one presentation about the scaling up of the materials, followed by the roundtable at 20 to 12, so in 20 minutes. Okay, thank you very much. Thank you. ¿No he visto la respuesta que me has dado?
Que yo no tengo contacto de ellos.
Pues es que si no llamo a Estíbaliz. Es que justo he pensado ahora, claro, si vamos a conectar antes de que...
Pero de todas formas, cuando estamos lo dejamos en silencio.
Sí, sí, perfecto. El YouTube se va a quedar aquí puesto en...
tenemos el... Vale, no sé si es una E o una E.
Esto es si no llamo a Estíbaliz, si vemos que necesitamos...
Va, además no es esto. Da igual, estaba poniendo el o sea que es... Madre mía, estoy cerrando. Y eso que ya me había convertido el link que me había mandado Estíbaliz en una cosa... Sí, porque vamos, es imposible. O sea... Volumen. Audio del equipo, ¿cómo es?
Ese es el, sí, es el auricular.
Vale, o sea...
Y el tech porque...
Vale, sí. Y la... Bueno, vamos a ver. ¿Avisaste a Estíbaliz para que nos deje entrar?
¿Le llamo?
Sí, llámala por favor, que yo no tengo su número. Ah, no, ya está, ya está. Pues ya están aquí. Vale. Entonces,
Sí, les podemos preguntar.
¿el micro es este?
Sí, auricular, fíjate.
Pregúntale-
El micro...
Ah, estamos silenciosos. Estíbaliz, ¿nos puedes confirmar que nos oyes? Por favor. Hello.
Estíbaliz.
Igual no está, o sea, quiero decir que
Ya,
igual
de
está
que igual
por
se ha
fuera.
ido al baño.
Está, pero no está por ahí, está de descanso también.
Theodore.
Sí, los escucho.
Hi, hello, Theodore, can you hear us?
¿Me escuchas?
We want to check
Estíbaliz, we cannot hear you if you are talking.
if...
¿Me escuchan?
Madre, here.
El audio tendrá que ser... Igual si no estamos justos el audio...
No, pero vamos a ver, espera.
El audio está bien y
¿No es este? El audio.
dale más el micrófono que el tech.
Hello.
Ahora
Hello.
tiene
No.
sensibilidad, o sea que...
Hello.
¿Y la salida de audio es
Pero
auricular
es
o
auricular, es que está cansado por aquí.
Sí, podéis poner los altavoces Realtek, pero te va a sonar
No,
desde el-
no,
claro,
we
tiene
need
que ser
to,
la que-
but ¿está encendido atrás? Porque
Hello.
el viernes, el viernes no funciona.
¿Esto se está viendo por YouTube o esto es...?
Sí, está ahora en directo además.
Pero verá.
Can you hear me? Hello.
We are checking...
Ah, vale. A Estíbaliz sí que se le oye por YouTube.
ok. The sound... vale, entonces estamos con las mismas de siempre. Si ayer se oía, se tiene que poder oír. ¿Está encendido ahí atrás la toma esta? Escucha, yo desenchufé aquí y enchufé también, te digo. El otro día porque tuvimos que mover la mesa. Hay un baño justo aquí detrás. Desenchufé, pero vamos, ese
Pero desenchufaste aquí.
Sí, abajo.
No,
Eso.
aquí no tendría problemas.
Salvo
El
que esté
audio,
mal
el audio
enchufado.
sale de ahí.
Eso es el... Claro, no, pues aquí no es...
El audio sale.
No, pues eso no lo desenchufé.
Tiene que estar operativo.
¿Podéis hablar, por favor, para hacer una comprobación? Could you please say something? Now you hear...
Ahora está sonando allí.
Well, we can hear you now, but we are going to test another option. Maybe now could you try again?
Yes.
Se escucha.
Yeah, it's okay. We are having the sound now from the speakers in the hall, but it's still very low tone. So we are going to try to increase the volume here. Could you keep talking or singing or saying something?
I'm not very good in singing. Okay, I will try to talk a little bit.
We are hearing you, but we are trying to increase the volume here. But at least we can assure that everything is going.
Let's move my laptop a little bit closer. Maybe now it's better.
We hear you now, so I think we can go in this way.
Okay, good, great.
Thank you. So we are going to mute this until the time of the roundtable, and thank you very much for being here today.
Welcome, thank you.
Vale. Entonces, ¿cómo silencio el sonido mientras tanto? Para que no se oiga. Da igual, lo pongo por otro sitio.
Es que por los altavoces no se puede. Te va a sonar aquí.
Bueno, pues lo que hago es quitarle el ruido aquí. Si es que se oye igual. Ahí. ¿Sabes qué decir? El sonidito este no se puede bajar mientras tanto y luego subir.
Bueno, sí, ahora lo puedo bajar.
Vale.
Pero lo bajo de todo y ya está.
Vale, es que si no. No. Vale. Bueno, bien, por lo menos.
¿Se oye?
Se oye.
Vale.
Sí.
Luego ya lo ponemos en.
Lo dejamos en...
Los dejamos así, luego movemos aquella mesa, la ponemos aquí y se emite a una visión general y lo que salga de la pantalla, que es al que esté aquí con el ¿vale? Te pones esto aquí y
Entonces,
ponemos aquella mesa.
Entonces ahora para la presentación funcionamos...
Vale, lo que está bien.
¿Está bien?
Así está simplificado, está bien ahora.
¿prefieres
Es que antes
explicado?
estaba...
Bueno, vamos a poner ahora en... tenías un... Bueno, dejamos esta más la primera.
Sí, o de hecho, si copias la última, la pones la primera, así es complicado porque
Sí.
la idea era dejarla, pero la puse la última en vez de la primera. Y luego dejamos esta durante la...
Vale.
Bueno, no, porque hay que poner en la cámara...
No, hay que poner la cámara aquí.
Así sale mal. Tienes que ponerla en extendido.
En extendido.
A ver. En extendido... Ven, un momento.
Tiene dos pantallitas.
F10. En extendido. Extendido es ampliar. Esta es...
Se la puedes cerrar. Espera a ver... Vale. No, pero esta es la
¿Quieres
presentación de
ver?
Scott. Esta es la que cerrar. Cierra esta. Sí, es que ahora la abrimos.
Pues
En cuanto...
la
ahora.
¿Que necesitas que no esté en modo presentación?
Y ahora ponle en modo presentación. Ahora no te llega nada. Claro, esta es la que no se puede ver. Pero ahora
¿Esta?
estamos al revés. Ahora está.
No.
Ahora tiene eso. No tiene. Tenemos las dos confundidas.
Pues sí, creo que... No, está abierta. Está abierta. Así, ¿no? Así. Está la
Sería lo mismo en los dos pantallas, no sé extendido.
Bueno.
Problemas técnicos.
Bueno, pero bastante
bastante
moderados.
bien, ¿no?
Sí, bastante, o sea, cogerme un micrófono para luego las preguntas.
Perfecto.
Vamos a probar de paso este. Porque luego... Hola. Vale, guay, funciona. Aquellos que están desconectados no los conectamos y tal. No, pero movemos. Pero luego sí que vamos a mover la mesa porque están 4 en la mesa redonda. Vale, pero...
¿Y si la movemos ya? y lo dejamos todo listo. ¿O hay un
¿Vas a darla
problema?
desde ahí?
Sí,
La
yo hablo
charla.
desde aquí. Puedo estar de pie o... Sí, sí, la movemos.
La movemos la mesa no sale, lo que no movemos son las sillas. Y quitamos los micros y luego ya movemos las sillas. Y luego ya la juntamos y eso, para juntarlas un momento.
Sí, tienes razón, que están tirando.
Estábamos levantando como jabatas. Bueno, luego ponemos... Las sillas no, pero las tenemos luego, las sillas sí como... Vale.
Podemos acercarnos si
Pues
quieres.
la juntamos.
Tendrán que estar frenadas las sillas, así verás.
No, aquí está rodando bien, lo que pasa es que tropiezan con todo lo que hay por abajo. Pero así.
Sí, vamos a hacerlas aquí y luego las ponemos en un momento. Y luego a Marta ya stop o a Marta ya tomates ponemos inalámbrico, las diademas y ellos funcionan con las otras. ¿Vale? A ver, mira, a ver.
Pero mira, yo
Al principio no salía entero, pero luego sí. Lo que pasa es que aquí, a ver. Con esto lo moví yo. Es que ahí está muy, como está muy aquí, no se ve la pantalla.
Ahí está bien.
¿Ahí está
Ya,
bien?
pero desde aquí no se ve la pantalla, esto va pero flipa.
Pero, bueno, no. Que se muevan.
Aquí,
Ponerlo atrás del todo.
aquí,
Atrás.
Ahí ya no te puede...
Ahí se ve la pantalla.
es que yo no muevo, pues no sigo para adelante. Porque debe tener mucha fuerza todavía, está muy nuevo y entonces no cuesta mucho abrirlo del todo. Y si no lo abres del todo, entonces te lo tumba.
De hecho no se mueve. No, de hecho...
A ver, cierra todo lo que no sea el Teams y esto.
¿Desea guardar los cambios? Sí, hombre, ¿por qué no? Vale, yo aquí
Tienes
no...
un ratón normal.
Vale, aquí hay otra abierta
Pues cierra.
y luego tengo ya...
Cierra todo lo que no sea el tuyo y el tuyo.
Esto no lo voy a cerrar por si acaso. Vale. Abro de nuevo la presentación.
Eso de todas formas está en el escritorio.
Office 2009, pues igual tenemos algún problema de verdad. Espero que no. Let's make sure that they can hear us on YouTube. So while we check that, thank you very much for coming back for the second part of the workshop. This will be a presentation in which I will be introducing what we do at EnviroHemp in the scaling up of different materials. And it will be followed by a roundtable where we will be discussing these different opportunities for carbon materials and, in general, hydrogen storage opportunities. Before we forget, and while we connect to YouTube, I'm going to pass to the people here some information about the project, so you can grab one and pass. That's right. Okay, so if it's working, YouTube, perfect. So this is the last talk, and it's a conversation. We can participate on this or later on the roundtable about how to go from laboratory to industry. The path from laboratory to industry is to scale up. And scale up in this sense is translating a successful lab process into a commercial one. Obviously, scaling up is just not making it bigger, it's making it work. That's the most important point, but making it work reliable, safely, and economically viable. And the scale up obviously is not linear scaling. The steps to go from lab to an industrial scale, usually there's an intermediate step that is a pilot phase. In lab scale is where, and I'm sure many of the researchers here know this part, is the proof of concept where you have small quantities, you have high control, and it's a low cost, relatively low cost when we go farther down the line. This intermediate step is the pilot scale where you test parameters and troubleshoot and optimize at a larger scale. And the idea is to have this medium step between the lab and the industrial where the end goal is the market launch. And I'm sure that we all have heard about the valley of death. The valley of death that happens in many startups and in many projects is where many good ideas that work in R&D, they get to prototype development, but die before getting to market because the pilot scale and getting to industrial scale is a tricky path. So first, I have some slides with general considerations when you are thinking about the scaling up a project, and then we will be giving a bit of lessons learned and specific examples of what we have overcome and achieved at EnviroHemp. The first thing that I want to talk when we are talking about general consideration is what could possibly go wrong, and the answer is almost everything. There are many things that you might not expect when you have a successful lab protocol, a product that comes out reliable, and you think, well, this is going to be easy to scale up. The reality is that you will find many hurdles that you need to overcome. For instance, and this is not limited to this, but equipment limitations. You are used to work in a scale in the lab. When you want to translate that into a pilot or industrial scale, very likely there's no equipment and you have to ask for a company to prepare or make something specifically for you. Some issues that you don't see in a smaller scale that are very obvious and easy, mixing or problems with heat or mass transfer, they become really big issues. Quality and reproducibility challenges are much bigger when it's bigger scale, and then you need to learn all the part of documentary and regulatory compliance. Important part to think when you are scaling, safety. Everyone's favorite topic, safety. New risks appear with a scale. It's quite obvious if you think about it. It's not the same if you have an oven that is 10 grams than 1,000 kilos, and you need to conduct thorough risk assessment and have a safety culture when you are scaling up. And what you learn is that small mistakes become big incidents. When you are in the lab and mix, 2 liters of 2 chemicals that shouldn't be mixed together, you might have an accident, which is a big issue and a minor explosion. If you do it with thousands of liters, then you have a big problem. Space considerations, when you are thinking about scaling up, something that you learn very quickly is that you don't work on your own. As scientists, you have your ideas of what you can do, and you can even talk to a company that can build for you some equipment. But there's much to it than just having the equipment. Is layout planning, utilities, workflow optimization. And what you need to do when you are scaling up is to work with engineers and architects. And this is a very multi-actor approach that you need to take when scaling up a process. And another general consideration that you don't realize is logistics. Very important to work with somebody that has experience in logistics and supply chain. It's much more complex when you have to work with tons of products than when you are working with small quantities, and then you realize all this import-export regulation, shipping, and it's really difficult to learn this communication with all the stakeholders in order to have a successful process at large scale. And the last one, financial considerations. Just a point, I put on Google rich scientists, and this is the best I could come up with. So just in case you are young researchers, there are not many rich scientists. But when you are doing this scale-up, you need to think about the cost of everything. Cost of equipment, materials, but as well labor and regulatory is very different. Finding sources for funding, grants, partnerships, investors. And when you are thinking about the scaling up a process, you need to think about it as an investment, not an experiment. And this is EnviroHemp. I'll explain a bit who we are and what we do before we go to some examples. We are a small company. We are located in the north of Spain, in Navarra. We are a small company that are very involved in R&D projects. We have projects in the European level. We are coordinators of a couple of Horizon projects, and we have as well some national and regional projects. And we focus on the valorization of byproducts and a scale up of different green processes, always with the idea of circular economy. In this R&D, we are presenting today this workshop is part of MAST3RBoost, which is the project of hydrogen storage, but we have other projects more related to biofertilizers, biochar. We have some other about activated carbon. And what we are going to use, some of the examples I think are more relevant to this workshop and to this institution that are a scale-up that we have done in the valorization of agroforestry waste to produce different biochar, hydrochar, activated carbon. In the regeneration of activated carbon that we have a technology is electroregeneration and, well, biochar production. So lessons learned, and I've divided this in these three topics, starting with char. All this scaling up process, we are going to follow the same lab to pilot to industrial scale. In the first step, lab scale, for biochar and hydrochar, we follow the same process. In the lab scale, what we do is to validate the process and characterize different products, which is much easier to do at small scale. In our case, and I'm sure that everyone here, we start with literature review, but we always do these processes in the lab as well. Sometimes if we have, we are part of a project like EnviroHemp, some other companies might do this small scale, or research centers do these small scale experiments, but we need to make sure that everything is validated. And for that, we just need what we are use a small pressure reactor, bench scale furnaces. And what we focus in this part of the lab scale is reaction parameters, yield, carbon contact. Basically, we want to know how the processes work in a smaller scale. And what we learn is the temperature, pressure, residence time, depending on the process. And this is the first step in scaling up. And in this scale, for hydrochar. what we want in the pilot phase is validate the process, so same that we do in the lab scale, but a larger scale. And here is where we start having some hurdles. Usually when we are scaling up a process, we need custom-built equipment. And that part begins, we are at EnviroHemp, a multidisciplinary team. We have people with undergrad in biology, PhD in chemistry, and different kind of engineers. And we work together and with the company that we build, we buy the custom build to create these different reactors for us, for instance. So the first things that we have to do is to design if we want a reactor that is with the specifications that we want. Although it doesn't seem from in the picture, but inside we wanted very specific things in terms of steering and temperatures and all these kind of things. And many things that you don't think about it when you are in the first conversations with a company that you are going to buy this custom build is everything that goes around any big equipment. You need to think about the pumps, filter, valves, electric panel, software control. That makes it more complex, and you have to work with software engineers in order to control the new software. You need to hire electricians that connect everything, and you need to have people that can pass the health and safety so you can use it, because obviously these are machines at high pressure. All that are things that are learned step by step, and in our case, some of the things that we didn't think about it, but you end up having to solve is, obviously you have the space for machinery, but the feedstock is much larger. Now we are going into more than 1,000 liters, and you need to have a space, just a storage for the feedstock, chemical storage. If you have 1,000 liters of an acid, safety. And then when you do the reaction and you have your first product, you have loads of residues that you have to handle. And these are the things that you learn with experience. In the biochar scale-up, same thing, validate process. We went to a company that built for us this medium scale furnace for biochar. And we learned basically very similar things. In this case, as well, we had issues with the quality of the product that was coming out. We have issues with how well sealed was, because we pay a lot of attention in making sure that the inside of the furnace was absolutely sealed, but where we were storing the product while it was still hot was giving us some issues. Anyway, this pilot phase, what helped us is to select the parameters and the feedstock that give us reliable results into the next step, which is the industrial phase. Right now we have at EnviroHemp this industrial line open that we are already manufacturing biochar, engineered biochar. I'm not going to get into that now. But we learned that even if we had loads of experience with lab, we did many experiments in this other furnace that you have seen of pilot. When we moved into manufacturing, there was still some work to do in getting consistency for feedstock and for the final product. And we had to work again, engineers that build us the oven and that put it together, all the permits to be in the line, software engineers, because engineers that we have changed a couple of times our software control, because we want to have more control about the process, monitoring as well with the emissions. And right now we launched last year our first product, which is a biochar that we are marketing right now for agricultural use, or people that can use at home. So this is a successful story of a scale-up process in which we have transformed different agri-food residues We selected a few, we made some changes to have very good yields. We have better yields than average for getting biochar, and we are very happy with our final product. But we did not stop there. Right now, as told you, EnviroHem has, we are working in different projects. This is another European project that we are coordinating. And this is a bit of an ad, since I have the opportunity. We are going to be working in using this biochar and tailor it for different other applications and give it more different uses. So we are asking for everyone here or that are in the workshop online to please sign up for this stakeholder register form. We are looking for SMEs, primary producers or researchers that might be interested in working with biochar. We have this project that started in June this year, and we have cascade funding, so there will be the opportunity to ask for mini projects within the project that can use or want to use further down the line biochar for different products or opportunities. So please register if you are interested in being in contact with us. The second one is scaling up activity carbon production. Very similar step from diverse feedstock, we want to get to high capacity activated carbon, kind of activity carbon that we have seen in the other two presentations. In lab scale, this for instance in the MAST3RBoost project is what CSIC and University of Nottingham, no, CSIC is doing in terms of the small scale. We can do this for some of the projects. Lessons that we learn. We need to control very much what happens in very small scale, even in the first step of scaling up. What is a small problem that the cake rises too much, and you have these few grams of product with, in this case, is a potassium hydroxide coming out, and it's a bit of a mess, and you have to clean up for a day. Even when you do it in the first, we still call this lab scale, 3 kilograms. That becomes more of a problem and more of a hazard if it goes over the resistance and all that. Then we go to the next step, which is the pilot. And for us here in activity carbon, we go from 3 kilograms to 20 kilograms. And there's many operational challenges that you are not aware until you do it. Some of them, if you think about it, they are quite obvious, but you need to live it. For instance, material loading and unloading. When you are working in 3 kilograms, one person can easily add a mixture or add products, not a big problem. When you are working with 20 kilograms, it's much more difficult, and you need to, thankfully we have our team that can build in the house different ancillary equipment for our safety, and we had to build a trolley to help us load the material into these trays. Once you are using the furnace, homogeneity of temperature, that's a really big issue. I'm sure it happens to an extent in a smaller scale, but in larger scale, really, really difficult to have an homogeneous temperature inside the furnace. And that is a big problem, because you can have part of the activation reaction that is at 900 degrees and other part of the oven is at 800. And that obviously causes problems with the homogeneity of the final product. You will notice there's a picture later of the furnace, but we don't show pictures of the inside of this pilot scale furnace, because we work a lot in where to get the heating elements and the disposition of these trays inside the oven to minimize these problems. Then gas purge systems for control atmosphere. We have a nitrogen atmosphere for this chemical activation of activity carbon. And we have had couple of small explosions, not really explosions, but say scares with the gas purge system. We have obviously many pressure controls inside the pilot scale oven, but even with all the precautions, we have had to tailor the amount of gas purge that we put before and during the activation, depending on the feedstock. So obviously it takes a lot of trial and error. And once you have this activated, then you have to separate, filter the material and get the activated carbon that you need or that you want. And this in the lab is relatively easy. You don't think twice about, I think that you pointed out, washing with hydrochloric acid. It's very easy. When you are doing it in larger scale, you don't want to mix the kilograms of potassium hydroxide left over with HCl, because that would be very exothermic. So you need to learn how to de-risk the process, but to get the final product. And that de-risking, usually what it comes out is with residue management, because there are many solid and liquid waste streams that you need to get rid of, and that takes time and money. Lessons that we learned in this scale-up of activity carbon. The most important goal for us when we do this activation, apart from getting a product that is similar results in terms of the quality of the final product to the smaller scale, is that we need to be homogeneous. What we call a process that works is a process that gives us a product that is homogeneous and we can trust. And it's very important that we take into consideration all the results obtained in the small scale experiments. That cake that I showed you before, we shouldn't have gone to a larger scale after seeing that the first small scale was rising so much. And in terms of safety, overpressure, what I said before, we have had this couple of times when there was too much pressure inside the furnace, and when you have that might be 3 meters by 3 meters furnace at 800, 900 degrees, you don't want to have these kind of issues. And we learn very much that operator training is key, and having safety documentation and safety training is really, really important when you are doing this scale up. And here is the oven that I was talking about. And in terms of logistics, similar than before, you need space for all the materials that you are going to be using, raw materials, chemicals, and as well waste, because it's very expensive to have a company coming every day to pick up all the waste materials that you have. So you need to think about that. Something that we have learned is the workflow design. You want to minimize cross-contamination. We work in different processes at the same time, and it is very important to think about where you are going to put all these equipments in what area you're going to put them. And sometimes handling equipment for this, the high temperature material, usually very heavy, as you know, and handling equipment might be difficult sometimes. And even at pilot scale, without getting to industrial, there is some legal side that you need to comply with that makes it, well, I'm not sure it's difficult, it's necessary, but you need to make sure that you are following all the waste management, emissions, and all the permits for this scale as well. In activated carbon, we are right now in the process of getting a patent. Cannot say much about it. Well, I don't know how much can I say, so I'm not going to say much, but it's a novel method for producing activated carbon from a variety of agricultural residues, very vague, although it's a bit more specific. Basically, what we have done with this lab to pilot scale up is we have a method that is more sustainable than traditional chemical activation for activated carbon. And with this, more sustainable because we use different reagents and ratios and temperature. Well, it's a bit, we have found like a sweet spot for this activation. We are getting activated carbon with high surface area, comparable properties to traditional methods. And this is the last scale up related to activated carbon, and is reactivation of or regeneration of activated carbon. We at EnviroChem, we have been working for years in electroregeneration of activated carbon. In this case, it's for granulated activated carbon. When the activated carbon has reached the end of its lifetime, you have two options, especially if you are a water treatment plant that has tons of activated carbon. You have two options. You just call somebody to take it to a landfill and get rid of it and buy new virgin activated carbon, or you can try to regenerate it and keep using it for another cycle. Usually this reactivation happens thermally at high temperature with emissions and with a loss of activated carbon in the process. And we have been working for years in electroregeneration of activated carbon to get to the same point. For that, we have been involved in two R&D projects, Portable Crack and Aceleron. The idea of this electroregeneration, before we go to the scaling up, is that the activated carbon goes inside the equipment where there is a liquid that goes inside, an electrolyte. There is a current that goes through the activated carbon. It's an electrochemical treatment that produces the desorbment of the organic contaminants that are in the activated carbon and their oxidation. After that, it goes to another part of the equipment where it's neutralized, separate, and ready to go back to plant. And we have worked on that from lab to industrial scale. So what I said at the beginning, general considerations, financial is important. So we did this development thanks to it was a H2020 project, Portable Crack, where we wanted to develop a portable electrochemical regeneration system for activated carbon. And this is already a part of the scale up from lab to pilot. We started much smaller than that because in this project there were some universities involved that did some of the very small scale, and we started with the deployment of this going towards the pilot in some tons of, not tons, dozens of kilos. We changed to inside, this is one of these shipping containers to make it portable, where we went going higher and higher until we ended up at the end of the project with this one shipping container that could regenerate around 1 ton of activated carbon every couple of hours. And that was a development that was during this project. This project had a continuation, that is Aceleron. This was funded by the Next Generation EU program. It was a CSIC Seal of Excellence. And what we did in this project was to scale up this technology that we got from Portable Crack into the next level. So even if it seems like we already had one shipping container, now this is the new Aceleron, well, portable MT, we call it, technology. Is in 2 shipping containers, and we went from 1 ton every 2 hours to 1 cubic meter, every 2 hours to 3.5 every hour, which is a big leap, and it was another part of this scaling up, and it took us more than a year to get to this new product that we have this as a service in the market as well. So I don't know how we are going with time. Probably we are good. so finishing now, key takeaways from all this long talk. Scaling up needs teamwork. You need to work as scientists or researchers with engineers for sure to be able to have everything ready to work, and business, the financial part is really important. If you are thinking about scaling up and you are working towards in this team, plan early for the safety logistics and plan ahead the costs, because they're going to be more than you think. In all these 3 stories that I told you, we have had surprises. You are going to have some unexpected results down the line. That could be scientific, like something does not work the same way at large scale, but sometimes it's logistics, and you discover that you cannot import a material at a certain scale that you need. So learn from them and expect them. But the reward, if you are able to scale up and go through the valley of death and end up with an industrial process, is that you have real world impact. You have a product or you have a process and you can see in the real world. So that's everything I have for the scaling up. So I hope that was of your interest. We are going to go now with the roundtable, and we can discuss this and everything we have talked about, hydrogen and activated carbon and absorbing materials. So please, if Marta, Scott, and I don't know if online, but Thomas as well. And while we are doing this, because I forgot to thank, and I will thank later to everyone involved, I want to thank as well Sebastián Correa from EnviroHem that helped preparing these presentations in a really short time. So thank you, Sebastián.
Es el moderador y vosotros compartís este y el de Manuel.
Vale. Estamos aquí. All right, so while we get the people that are joining us online, let me introduce to Tomás González Rodríguez, who's joining us for the roundtable. Tomás holds a degree in chemical engineering from the University of Oviedo and has a master's degree in chemical technologies. He's worked at INCAR in the development of composite materials and in the United Kingdom carrying research in the aerospace industry. So welcome to the roundtable, and we have Theodore Steriotis. I don't know if you can hear us. Perfect. Who is the project coordinator of MAST3RBoost. Is one of the other projects in the same, was awarded in the same call than MAST3RBoost. And Zakaria Belfkira from MAST3RBoost as well. That is joining from Mohammed VI Polytechnic University. I don't know if you can hear us.
Yes, I hear you. Thank you very much.
Perfect, thank you very much. So are we okay online? Okay, so this is going to be a roundtable open for discussion. People in YouTube can post any questions or comments in the chat, and we will be answering the questions as well. Okay, so let me get that ready. Okay, so I'm going to start asking some questions, starting with you, Thomas, joining us. We have had a brief discussion before about what's your work and your opinion of this possible use of carbonous materials. So do you want to just give us a bit of your overview
Yes, I was mentioning before that I was not working on hydrogen storage for mobility, but usually it was for industrial plants or energy production. And in that step, the things that they are going to ask you is some of the things that I got it from Martha's presentation. It's the temperature, the pressure, the weight that can be stored. But then there are things like we were talking about some kind of balance of plant or the boiling off that you have because you are working at very low temperatures. That's something important to take into account for later for the simulations. Also, you gave information about the depth of discharge because it was not coming, all the hydrogen that was absorbed, it was not coming out. That's good, but do you have any information about the degradation over times or cycles working? Because that's another important point, and also a roughly estimation of the cost, because with all that view, they can make like simulations and get levelized cost for the hydrogen.
Yeah, thank you very much. Yeah, I can start with the cost, and then I think that Scott can answer about the cycles. We are really far from deployment of this technology in the cryosorb. Obviously, the cost of this first prototype that we are doing in 22 liters is out of this world. and we are doing studies. Part of the project is an LCA and LCC to get to know the cost that could have in the future. So we don't have that yet, but still it's going to be very expensive, especially if we take into account how much it costs to build these two vessels that we are building and all the materials. But I think that answering to your question, we don't know the cost that it's going to have, but it's going to be too high for what the market expects in the near future. And yeah.
So yeah, I can talk a little bit about cycling and aging. I might be wrong, but from what I could tell, there wasn't anything in the literature to base the cycling experiments off of. Not for this kind of system, at least. So I did the what I think are the first set of cycling experiments. We had 5 samples. 3 of them activated carbon and 2 moths that I selected. For the cycling experiments, we had some trouble because, as we said, you needed to, in theory, you should be cycling both pressure and temperature. When you're cycling pressure, this is no problem, but the temperature, the charging temperature was 77 Kelvin, whereas the discharging temperature is 80 Kelvin above that, 157 Kelvin. As you would have seen from the presentation, there are several temperature control apparatus. And the cryofurnace, which allows you to go to 100 Kelvin, does not go all the way down to 77 Kelvin. So, of course, I can change the temperature control device when I'm there, but at some point I have to sleep. So we instead had the cycling with the same temperature differential, but raised up. So starting at, I can't remember exactly, but something like 130 Kelvin up to 210 Kelvin, with the same pressure differential. And then, so we were able, okay, so then the further practical issue is this relies on a cryofurnace, which relies on having a constant supply of liquid nitrogen to the cryofurnace to control the temperature. This was also problematic because despite what the instrument manufacturer says, the gear that they provide does not last overnight. It lasts maybe 8 hours, maybe 10. So this meant that actually, you think you're going to get, 15 cycles or something over the course of 24 hours, but in the end, maybe you get 10. So as a result, we were basically able to perform something like 40 cycles, which is not sufficient for the lifetime of the material, but nonetheless, we performed 40 cycles. Maybe that's a year's worth of the material, maybe. And we saw no change in porosity or hydrogen working capacity after these cycles, which is positive, but I think there's a lot more work to be done. We also did aging tests, which are much more conclusive, because we were able to simulate aging using an accelerated aging test. I think they use it in like the same in like pharmaceuticals or packaging, where you basically heat the material and then measure the properties of the material at various intervals, and you can basically extrapolate that to be a longer amount of time at room temperature. Again, no significant variation in porosity or hydrogen uptake using this, which is great. So, and that was up to 5 years under air, except for one material, which was a metal organic framework that had a binder, which gives some crazy results and seems to improve and also the properties. So it's I think this is something to do with binder, but in general, we can see from our results thus far with both the MOFs and the activated carbons, there isn't any problems with aging. Cycling needs much more work. Does that help?
All right, thank you very much. And now the other two people that join us from the roundtable from MAST3RBoost. Because starting with Theodore, a bit a question related to what Thomas said about cost, and how do you see the perspective of deployment of this technology into the real world?
Yes, first of all, I would like to thank you for inviting us in this very interesting workshop and this discussion. The sound is coming a little blur in my laptop, so maybe I don't catch everything that you say. Now, let's say we are in an infant state, I would say, for discussing the penetration of this technology in the real world, cryogenic storage of hydrogen. But there is certainly some space for this technology. And in our opinion, it has to do with larger and larger systems. So perhaps the car is too small for this technology, but larger vehicles, let's say train, buses, trucks, even maritime applications, there seems to be a good window there to try and penetrate and see how this can be meaningful for such applications. Nevertheless, I say again that for the moment we're a little bit far from the compressed gas or even the liquid storage.
Yeah, I think that we can all agree as possibly right that like the applications are really difficult for this technology to get to market. There is possibly a space for heavy duty. Yeah, thank you very much. And yes, Zakaria, part of the MAST3RBoost project as well.
Yes. Yes.
What do you think are the main technical limitations in your experience for this technology?
First of all, thank you very much for the invitation. I'm very proud with you today, and thank you very much for all clear representation and consistent presentation and all technical information shared today. For me, I work a lot on simulation and on the design of the tanks and storage tanks and all this stuff. I think that's the major problem is, for my opinion, there is mainly terms. The first one is that what concerns the thermal management inside the tanks, because as you know, absorption is very high exothermic. So when we want to charge, for example, we store hydrogen with adsorption, we generate a lot of heat. So for my opinion, this is a very challenging issue, given that we need to find some solutions, some real solutions to avoid these kind of problems in our storage system. The second technical issue, I think, is the scale up, as you mentioned in the presentation. Scaling up, even the adsorbent material is not so easy. So especially when we're talking about MOF and when we talk about something green. So for me, this is the two major technical problems that we can say about this kind of storage. But as Theodore said, this methodology of storing hydrogen is still in its beginnings, and needs a lot of effort, lots of research, practical thinking in order to have something that we can use in mobile transport or in other area. So this is globally what I think about this. I don't know if you have some answers about this especially the first issue about the thermal management in your project, or you don't have or if you have any idea about it.
Yeah, and thank you, Fabián. Well, true that those two challenges that you pointed out are really important issues. About the adsorption being exothermic and very energy intensive is a problem that is difficult to overcome, but we are working towards this design of the vessel, trying to minimize that and to absorb the impact. And the second one, I think that is really important, is really what we are talking here in this roundtable, is about the absorbent materials. And you pointed out the scale-up problems that we face with you in your case with metal organic frameworks, but here with activity carbon as well. So I don't know, maybe we can deep in a bit more into this topic. Everybody is welcome to join. I've seen that you, Marta, have like really good results of these activity carbons, but how do you see a path for scaling up those materials?
I think that the main problem with CO2 activation is that the generation of porosity is based on carbon atoms etching. So at the end, if you want to achieve really high values of surface area, your yields are really low. So we need to develop alternative activation strategies that can generate porosity through other measurements, not just by removing carbon atoms to increase the yields. And also in the case of biomass, it has also an intrinsic problem of not having by itself a very high carbon yield, so that's another challenge.
The yield definitely a problem.
Yeah.
And then the problems comes with the scaling up in the future, because the cost of some of the materials that you presented are probably too high to make financial sense. Some of the polymers.
Yeah, that would be for the case of the potassium hydroxide activation. They are sustainable, but yeah, in some of the cases the cost is quite high.
Yeah, I don't know if very open now to comments, suggestions from everyone on the table. Any other main challenges that we see in this technology?
I can comment a little bit about the question about the cooling of the vessel. Obviously, that's not my area of work, but I have had conversations with both Spike and EDAG, who have been working on the simulation and design and then the actual building of the vessel. And they've had, you're right, they've had to come up with quite innovative ways to actually cool cool the vessel. Unfortunately, we don't have a diagram of like a 3D render of here, unless you happen to have one on your laptop. And I don't know how much it would help anyway, because I didn't design this, so maybe I would point to the wrong thing or whatever. But basically, what has ended up being necessary to happen is that there are inlet pipes for the hydrogen, but there are also inlet pipes for the liquid nitrogen. The quantities of liquid nitrogen that they figured out that they needed to use were very, very large, like tens of liters, just to do to cool it down for one time. And then also you need to heat it back up, so you need someone to evaporate the liquid nitrogen as well. So it is a challenge, but I think fortunately liquid nitrogen is very cheap. So one of the cheapest things in the lab that might mitigate that issue.
Yeah. Any other questions, challenges?
Maybe I can comment a little bit on this. Indeed, the cooling is a major problem, and more or less because we are proposing a technology that is supposed to be fast, let's say. So when you need fast charging, you have to very quickly dissipate heat, and you know, our materials, both the MOFs and the activated carbons, are highly porous, so in principle they don't contact heat that easily, and moreover you need to keep your system constantly cool. So in my opinion, in order to have this let's say process to make it viable, the whole supply and storage systems, even in the hydrogen stations, refueling stations, should be completely different. So, for instance, hydrogen can be stored at the refueling station at cryogenic temperature. This would make things much easier. Instead of trying to instantly cool the hydrogen as soon as you charge. So the whole supply chain and storage should change for this technology if this is to be viable. Then for the scale up, my comment is that if it's difficult for carbons, for MOFs it's a nightmare. And this it's based on a very simple fact that the major solvent that almost every MOF is prepared in, is synthesized is DMF, which is now banned all over Europe. You cannot use it anymore. So we add to the scale up an extra step that you know, the synthesis conditions should be made in a green way. And this indeed is a major issue. So there's another step, let's say, in the things that you presented, the lab, the pilot, and the production. There is, let's say, from the lab to the pilot, there is the green step, how to change your solvents and your process to make it viable. You simply cannot upscale with DMF. It's completely out of the question. So this makes things a little bit more difficult for the metal organic frameworks.
Yeah, absolutely. And I don't know if Theodore or Zachary, if you want to tell us a bit at what point you are in your project, because there was some questions earlier about this feeling, how it will work in a car or in a bus or in a train, the time that will take to fill up the tank and the release speed. I don't know if you are in a point in your project where you are already testing this with your materials.
Let's see, our target, we are, let's say, we have set up our project based on a train. So the test case is a train. And the requirement there is fill up the hydrogen. The specific train has around 300 kilograms of hydrogen per day, and you need half an hour to fill it up. So this is this comes from the specification of the compressed gas. So we need to stay in this area. Now we will, of course, we will not do such experiments with 300 kilos of hydrogen, so we do it on paper, and Zachary actually is working on this chapter, let's say, of MOST H2. The major problem is heat dissipation, so we have devised some let's say, heat exchanger systems that may help us, and we have seen that, at least in paper, it's possible to keep time within half an hour for the tank to be filled, but of course a weight and a volume penalty, because we need to use these heat exchangers. Unless the whole process is completely different, and then we use cold gas to fill the tank. This would make the life of cryoadsorption much easier.
Yeah, absolutely. I don't know for activity carbon, because we are not in that stage, we are not doing the real tank yet, but do you see any possibilities, or maybe challenges, problems, or possibility of increase the speed in which the filling related to the adsorption itself on the activity carbon? Do you see that as a problem? I don't know, in your cycles that you have done.
I guess with my cycles, I was limited by the ramp rate of the machine, so I wasn't actually examining this directly, like how quickly everything would equilibrate. And what else? Oh yeah, and besides which, I'm using 50 milligrams of sample. These kind of considerations about the reaction being exothermic, etc., don't really come into play apart from equilibrating of the weight. But yeah, I unfortunately I don't have any experimental data that's particularly useful in this context.
Yeah, don't know, you wanna? Okay. Well, this is a very open conversation with has any comments, doubts, or something I want to add. People online or here, very happy to hear. We have a question.
Maybe I can add another big problem that I see in all the, let's say, solid-based storage methods, which is the packing efficiency. This is also a major concern. You see, in most of the cases, you have a tank and you have a certain volume, and then you put a material inside. But when you put you lose probably 40% of the volume, because your packing efficiency cannot exceed, let's say, if you have particles, cannot exceed 65%, something like that. On the other hand, if you pack your material in a single molecule, I don't know, then you're bound to have diffusional problems. I mean, you have a huge particle, and then diffusion starts playing a role. This is also, let's say, a chapter that we should be looking at in the future. Let's say efficient ways to increase the packing efficiency in order to not to lose that much volume. Even if you have a perfect material that has, 50 grams per liter or 60 grams per liter, then if you use 60% of this, then you lose a lot.
Yeah, absolutely. And there is a balance in which how much you can densify the material before it loses the adsorption capacity.
Exactly. If you try to densify, then you might lose some porosity. You will lose some porosity, and then you start having other issues. So these are all problems that you know. Well, when you're working lab, perhaps you find a perfect material, an excellent material. But when you put it in the context of the process, then things get complicated.
Yeah, absolutely true. So we have a question here in the audience.
It was a comment. Thank you very much for all the talks. It was very interesting. And, well, it's outside of my field, so it's nice to always learn something. I'm curious about how did all the project go? Because you have so many different parts working in something. And in my head, it's like very difficult that all of you go into the same direction instead of each one going into its own interest. So I don't know if you can comment about the experience and what have you learned and what you will do differently for the next big project or those kind of things.
Sure, I can answer. I'm sure Theodore can as well. This project this size with 14 partners from different countries, it can be a bit challenging to be able to get to the results we want. On a personal note, there are projects that are much easier because the partners are very involved in the project and make it go further without much intervention from a management perspective. But the way that the projects are usually divided is with work packages, and each work package has an objective and a goal at the end. And we are now, I think that the work packages related to Azure materials work really well in this project, for instance, in MAST3RBoost, even if there was many issues because the machine was not working and we couldn't measure, and machine learning, the company that is doing the machine learning said like, well, I don't have enough data, and you know, but that happens in research and it's not very easy and linear. And now we are going to put together kind of the two lines, absorbent and the vessel. And I mean, don't want to brag, but the absorbent materials, they are already, and the vessel is a bit behind. The challenges here are usually linked to how much the partners care about the project. In our case, I think with MAST3RBoost it's been relatively easy, and we are going to get to the goals. They all have been, all the milestones, we have been more or less on time. The vessel is a bit behind for some safety concerns, that, and that's why the safety testing is happening now. But basically, answering your question, dividing the work packages in work packages, and at the end, just putting all together. Then, Theodore, if you want to add something else from your project.
Maybe you can repeat the question. I'm not sure I got it correctly.
Oh, just how this project, multidisciplinary projects, how is it managing and being able to get to a final result?
Oh, that's another nightmare. So in our case, and probably your case, but in our case is more evident. There are completely different. So the people that are synthesizing the new MOFs, for instance, they are interested in atomic scale details. You know, they fight with atoms and molecules, and they can produce some milligrams of the material, right? Then you have to carry this to the next stage, to a different group of people that can do it in kilograms. And then you need to use, let's say in our case, a company that produces huge tanks, cryogenic tanks, cubic meters, and then convince them that they should downscale their production. So there are completely different worlds that should be unified. It's a multi-scale problem in our case, because you start with a molecule and then you end up with a 2 meters high tank, and this is not straightforward. I don't know. It depends on the people. Actually, it depends on the people in reality. If the different groups are willing to cooperate, then things are easy. You can always find a way to make it work and carry on the knowledge from one scale to the other. So I think it's a difficult task to unify the different, let's say, length scales or mass scales in our case. But since it has a linear, let's say, approach, you start from the lab, you make you formulate it, and then you upscale, and then you put it in a tank. If you manage to convince people to work towards the next step, then things go well.
Yeah, absolutely depends on the partners. And from your side, as a research center at a university, what do you expect to get when you get into this multidisciplinary 3-year, 4-year-long project? What are your expectations? What do you want to get out of it?
Well, you always want to see that you can develop something that at the end can be used commercially. And in this kind of project, get the perspective that you cannot have in a lab from the industry, for example, or going to a larger scale. That there are many problems that you don't face in the lab, and that you have to think about it, because that's maybe you have a really good material, but at the end you won't be able to scale it up. So
to have a bit of real-world perspective into this, because I guess that when you go into this kind of projects, you want to have research papers out. Is that the main goal for you when you go into this project?
In this kind of projects, normally no. Those maybe projects more related to fundamental research. But here you want to see how to translate your material into a real possibility.
Perfect. Any other questions from the audience?
I have a question related to the LCI analysis, because we are making that analysis in our project, and we are trying every time to use renewable sources and processes as sustainable as possible, reducing the use of toxic chemicals and so on. But we are maybe not sure about how far are we from the other processes in this item. I mean, are we really decreasing the toxicity of our materials, or processes are really as sustainable as we believe, or not? I have that doubt.
In general, or
in general, yeah, because we are using biomass as source of carbon or biomassic products, and in the case of MOS, we are using residues as well. But we need to treat them, and I know that LCA analysis was a difficult process for us. So I don't know finally the results of that, if we are close to the real things or not.
Well, I'm going to repeat the question a bit, the question just in case you couldn't hear. It's about sustainability of the process, and how sustainable are we being in this project, at least in the MAST3RBoost project. I don't know, in MOST-HU, I guess you are doing studies as well. So we are advancing towards being more sustainable, and the fact that we are using residues or byproducts to create these absorbent materials is a good step. However, the processes are not clean processes. They all use chemicals. There are ways we use high temperature. So I don't know if we can see a way of being more sustainable, changing the energy that we use or the chemicals that we use. But there's not much, unless, I don't know, other opinions here, that we can do to be more sustainable. The LCI and it will tell us how far we are, but there is a leap here that we have no how much energy it will need in an industrial scale. So there's a bit of an assumption that we are doing there. But I don't know if there is, do you see from the technical point, how can we go more sustainable?
I mean, I haven't ever done this in the lab, but as far as I understand, you're still on the scale up, you're still using conventional heating, like thermal heating. There are studies which use microwave heating, which means that in theory there should be less energy used there. But I haven't seen, this is for activated carbon production, not MOFs. But I haven't seen them yield the same kind of results as we are getting through conventional heating. So that, yeah, but that's maybe one route of investigation. There are also other ways to reduce the amount of potassium hydroxide that you use. But again, not giving as good results. So yeah, it seems like we're always, for any kind of improvement in sustainability, we're basically reducing the porosity of the material most of the time.
Yeah, just finding the balance between.
Yeah.
I don't know if for MOFs you already mentioned a bit of DMF.
Yes, but sustainability is a little bit more complex than material synthesis, let's say. Depending on the context you are looking at it, for instance, what our LCA people have covered is that the cost of the material or the environmental cost of the material is minimum compared to the production of hydrogen, for instance. So if you look at the whole cycle of hydrogen, then using a material which is more or less sustainable does not make a huge difference. Then if you look at the process, it's another level. Let's say somehow we manage to store the same amount of hydrogen compared to a 700 bar pressurized tank. So we gain 600 bar energy, compression energy, let's say, each and every time that the tank is filled. That's a huge gain, if you consider, depending on the cyclability of the material. So if you have a material that you can use, let's say for 1,000 or 10,000 cycles, it makes a huge difference compared to not having a material at all, because you simply gain energy from not compressing that much. So in this infant state, I would say the synthesis itself should not bother us too much, in my opinion, because if it's successful, then the gain, the overall gain in the process and so on is much larger.
Yeah, I do agree that we are not in the time to start refining the process and trying to change that, but it's always good to have a starting point, trying to be as more sustainable as possible.
Yeah, sure.
So, Thomas, you that are an external to both of the projects that we are working, we are obviously a bit biased to this technology.
There was another point regarding what he was mentioning right now. When you got the tank, the Type 4 at 700 bar, when you charge it, you come from a higher pressure, and you also need a heat exchanger to cool it down. Also saving in that.
To the process, yeah.
Yeah.
So I don't know, you as an external, that you have seen a bit the results from MAST3RBoost the general idea of what we are trying to achieve. What problems do you think I'm not sure if the public, but the market will see, apart from the cost that we have talked about this idea of using cryogenic hydrogen?
I see the problem of the heat exchanger, as you were mentioning before, because the absorption, you need to evacuate that heat. What are you going to do with that heat at that low temperature? I see that's a problem. You need to also carry like a energy balance from the energy that is stored in the hydrogen, the 33.3 kilowatts per kilogram, how much you lose in all your process.
Yeah, that's
with boiling off, with all the balance of plant or whatever. And I've seen for big transport, for the maritime transport, there are also companies that they got commercial products for ammonia, and they got crackers for that ammonia with special membranes with palladium, and to get hydrogen and nitrogen, and it's got like a 75% efficiency. So you have to check, because they would be like competitors, especially for that.
Yeah, absolutely. Yeah, chemical storage is another competitor, definitely.
Yeah.
Yeah, one of the points that you raised and is about energy and low temperature is the main issue we have here. Do any of you to see possibility of activity carbon being used at a higher temperature? Do we have a bit of possibilities there of changing the temperature?
I mean, I think I'll probably say the same thing as you. I mean, at 100 bar and room temperature, getting above 1 weight percent it doesn't happen. It's not, you basically have no usable hydrogen stored at that point. So yeah, unless
you need to increase the absorption strength in inactivated carbons, and that also happens, for example, in some MOFs, but there are others that have open metal centers that can show a good hydrogen strength at low temperature. So maybe trying to simulate something similar in inactivated carbon, introducing, for example, the materials that are nowadays being investigated a lot, the single atom catalyst. So maybe something similar with carbon materials can improve the storage at ambient conditions.
But and is there a middle of the way? Maybe not room temperature, maybe not cryogenic. Do you see any path in the middle where I guess that 100 pressure is something, the 100 bar pressure is something that we decide that could 150 and a bit higher temperature. Do you see activity carbon working in that range?
Well, it depends on the kind of porosity that you have, that even though you increase the pressure, you are not going to get more hydrogen absorption. You will just have hydrogen compressing your pores, so it's not going to be efficient.
That's even going to go worse. So we just basically can play with temperature if we do something.
Yeah, but it's the challenge of the strength of the interaction between the material and hydrogen.
But actually, kind of a tangent based off of that idea of, like, okay, can we change the conditions to get, I guess what we're looking at there is we want a certain working capacity for the material. In this case, 10 weight percent or 40 grams per liter. So you, in essence, you want to the least harsh conditions for this working capacity for your material. So there may be a quicker way of determining what those conditions would be. So what that temperature pressure swing would be. I've been because right now you're kind of working on trial and error. You're like, okay, what if we do 150 bar and 100 Kelvin instead of 100 bar and 77 Kelvin? So I've been working on some theory that allows you to predict adsorption isotherms, and if you can predict adsorption isotherms, you can actually predict a an absorption surface, so you can predict loading as a function of both pressure and temperature. So it's a 2D kind of plot. I wish I don't have an example of it here, but it's like a heat map essentially. And so in theory, I mean, depends how good my predictions are. They're pretty good for about 50 Kelvin difference or so. But in theory, you should be able to look at that and select the conditions that you want. Select the conditions that are the least difficult to attain to get the working capacity that you want.
That's very interesting. It definitely opens the possibilities, and it's going to help to pinpoint the best condition for that material. So going a bit technical, and after that we'll finish with a bit more of a general overview and the EU landscape. Going to the presentations that you both did about the activity carbon, I have a question for you, Scott, about the volumetric measurements. You put in the presentation that the more points, there was more uncertainty. That was an interesting point I would like to clarify. And the second, related to the same, the BET measurements, how accurate are in general, these measurements and comparable between research? If you have had these issues when working collaboratively with other centers? Yeah, this.
I'll answer the second one first. I could go on for quite a while about BET theory, but I won't. But suffice it to say that, and this is my own work, this is based on some work from some people that I work with, but BET, there's a few things that people should know about BET theory. The first of which is it's wrong, and it doesn't measure surface area. It measures something which is useful as a fingerprint. It does measure surface area for some materials. It doesn't measure surface area for microporous materials for reasons that I'm sure a lot of people in this room will be aware of, based on some assumptions that it makes. But I don't need to go into that. BET theory is also historically and still to some extent applied inconsistently across research groups. So for microporous materials, there was a set of rules devised by Ruckerol in the early 2000s, which were great because actually it gave you more consistent results than the previous method. But actually, even with that, if you actually followed the letter of the rules, the same isotherm to 10 different research groups and get 10 different answers. And these results would vary by, they've shown in some work that these results could vary by as much as 100%. So not great.
Not ideal.
No. So the innovation in the last few years is a piece of software and an algorithm called BETSI, which is the BET surface identification, which basically says, okay, we're not going to let the humans mess this up, and we will put the data through some software, and it gives you the optimized BET area. And I would highly recommend that if you're measuring BET areas or determining BET areas, then you use BETSI, because at least you can blame the computer if it's a strange result. So, and this is quickly being adopted as the standard. What was the other question?
Well, it's about the uncertainty, so kind of...
the uncertainties in volumetric. So, as I understand it, maybe it's easier to talk about why there's less uncertainty in gravimetric, and then I can work backwards to volumetric. So gravimetric, all you're doing is measuring the weight of the sample. So every measurement is basically unique. It's like every measurement in your isotherm is its own measurement. Whereas when you are measuring a measuring volumetrically, then you're increasing the pressure by some amount, and then your pressure that results after the system is equilibrated, in order to determine based on that how much the was absorbed. So that means that that every time you measure a point, you carry over the uncertainty from the last point, and so that accumulates. So when you so it doesn't matter as much, fortunately, for lower pressure experiments. So like the classic BET experiment, it's kind of fine. But when you move to high pressure experiments, then they actually recommend for volumetric measurements that you limit the number of points that you have in your isotherm, so that you don't basically exponentially increase the uncertainty. I hope that explains that. I haven't done volumetric high pressure measurements, so I'm maybe not the expert on that. But, yeah.
Okay, no, thank you. I don't want to steer the room, but I don't know if here at INCAR, do you use much BET or?
Maybe I can also comment on that.
Sure.
So historically, BET was written for open surfaces, so no pores. Marginally, they use it for mesopores, which is less okay at low pressure. It's completely wrong when we are talking about micropores. So one thing that we should all know is that there's no connection with this number, the BET area, with the surface area of the material. So people are using it still because it provides, let's say, as Scott said, let's say an easy number to give you an idea of how much your material, let's say, what is the extent of the solid gas interface, something like that, how good it can go. Using Betsy, as mentioned, is a way out because you let the software decide on the points that should be selected. But again, it's in opinion not always connected with the performance of a material. In some cases, it's highly misleading to use even the BET area, even the Betsy area. Now on the volumetric gravimetric, there are certain, let's say, pros and cons for each method. Let's say for manometric systems, it's if you have a leak, then you're doomed. Everything is completely wrong. In gravimetry, this is not the case. You may have a small leak, and everything goes well. Especially if you're working in pressures. On the other hand, if your hydrogen is not extremely clear, and you have adsorption of some contaminant, for instance water, then this effect is much more heavy in gravimetry, because manometry will not understand any pressure difference from some ppms of water. Then it's the heat transfer issue. In most manometric systems, your sample is in contact with liquid nitrogen when you are measuring cryogenic conditions. So you're sure that your sample is at 77 K. In gravimetry, on the other hand, your sample is standing in the middle of nowhere, and it's connected with a liquid bath through the gas. And depending on the size of your reactor, let's say, this might be a major problem. So you have a limited heat transfer from your sample, from the liquid bath to the sample. So there are many things that can go wrong either way. I would say that if a lab can do both, then it would be the case. But in any case, each lab, regardless what method, should always, in my opinion, measure a blank, perform always blank experiments periodically to check that indeed the absorption is zero, for instance, in a volumetric, in a manometric or a gravimetric system. Actually, in my opinion, in scientific papers, these blank runs should be reported as well, always, to also check, what you're measuring.
Yeah, interesting. I don't know if here, INCAR, you have had these issues as well when sharing results with other researchers, when comparing results, or what do you see in the future instead of BET, if that's a problem?
Well, it's unluckily a well-established methodology that is used, and it's true that you have to keep in mind that, and sometimes it's called apparent surface area because it's not really a value of the surface area in certain materials, especially or in particular in these microporous materials. And in fact, if you check, for example, the correlations that I saw between surface area and uptake and pore volume, they are more or less or exactly the same. If you represented these materials, the surface area against the pore volume, you will get a straight line because in this case what you are doing really is translating the pore volume into surface area. So you have to take that into account, but it's true that it's useful to compare in other materials with other materials, but taking into account and remembering the limitations that it has.
So it is to get an idea, but we don't have to take it as the final properties of the material, I guess.
Can I make it further?
Sure.
Okay. Or are you done? So, I mean, this is more of an opinion, and it's maybe an opinion from some spends too much time on computer looking at absorption isotherms. So I think the reason that BET theory came about was because, well, one of the reasons is because it was a relatively simple way of determining surface area for non-porous and then mesoporous materials. And then, of course, people use the surface area that we determine via a nitrogen isotherm as some sort of indicator of various properties, but including high pressure gas storage capacity. But what we're doing now is we're taking one isotherm and extracting a value from it to predict another isotherm, or to indicate another isotherm, or a value from another isotherm. So it seems to me that we're going through different steps. We're going through a strange amount of steps when we're just basically measuring two isotherms. And then, so sometimes what you do, because okay, maybe the BET area doesn't correlate that well to the hydrogen uptake at 100 bar, is that you go and you make a pore size distribution, which is it exists. That's a thing that we can do. I have done quite a lot of work in like, I publish work based on pore size distributions and you doing kind of unusual techniques to determine the pore size distribution, etc. I'm not totally convinced that this pore size distribution, the way that we're doing it, actually indicates anything. Like, it indicates something, but I don't know what. I don't know what it's actually telling us. All that to say, we go from one isotherm at lower pressure with nitrogen at 77 Kelvin to another isotherm that goes up to her, also at 77 Kelvin, different gas. In theory, you should be able to reduce the first isotherm, this nitrogen isotherm, down to a set, hopefully a handful of scalar numbers, just single numbers, and also do something similar with your hydrogen isotherm up to 100 bar, and be able to then put that through machine learning to make the prediction, or to make the connection. Like there should be like a mathematically explainable connection between the nitrogen isotherm and the hydrogen isotherm, right? But nobody's made one yet. Nobody's made an equation that says, okay, if you measure this one, then you can expect this. Does that make, is that clear?
Well, there we have an opportunity.
If anybody will fund me.
Well, just outsider perspective, this is a really interesting scientific conversation, and really interesting that people that you are working on these materials have this maybe challenging what is established, and that's how things move forward. So really interesting. From outsiders' perspective that we use this number. We talk to people in the industry that use activated carbon for their filters, and the way they test if the activated carbon is still working is they do a iodine test or hexane test, very basic and easy to do in a lab, and then we talk to them and say, oh, you can do this surface area test with BET, and they are really far from that. So even we want to make it forward. I think that the users out there are really far from that discussion, but it's really interesting that it happens, and maybe it should change. So we have 10 minutes left of the roundtable. I don't know if anybody wants to have a topic to discuss here in the panel or the audience. So I would like to, if nothing else, talk a bit about, and going back to all this workshop of carbon materials, and I would like to gather your opinions about this technology. We have said similar with MOST HE, low TRL, far from deployment, but we are advancing on materials, in different absorbent materials. Do you see this research that is being done here with these European projects can be used in other areas with other gases, CO2? I don't know if other gases that you might be thinking of, I don't know if you know projects or you are working actively on something similar?
Sorry, but I'm not working on that part.
Okay. Then do you see for activated carbon as CO2 storage or CO2 transport?
Well, yeah, for CO2 capture, they have to possess quite similar pore size, for example, to hydrogen. So they could be also used, and also another widely established use is, for example, in supercapacitors, and also nowadays they are also being translated into hybrid capacitors and also some kind of batteries where you also need a certain design of the pore size distribution and also a very large surface area. There are many applications in which this kind of porous materials can be used also with success.
So this research could be translated into a different area, even if it's not hydrogen storage, that we are doing here.
Yeah. Yeah, for example, one of my PhD students is also studying some of these materials in supercapacitor electrodes. So.
Yeah, interesting. And I guess that for metal organic frameworks, something similar.
Yes. Well, one obvious, let's say, side process is natural gas storage. In my opinion, the same structures could work because it's again typical gas under pressure. So the same materials can work for methane, for instance. On the other hand, to go to CO2, you need a completely different structure. Then you need, depending on the concentration of CO2, you need much smaller pores, in my opinion. So both in MOFs and carbon. So it's a new chapter. It's another set of structures that are relevant for these. And for supercapacitors, they say, I'm not an expert in this field, but they say that you need some hierarchical porosity. So you need also very small pores and large enough to facilitate transport. So maybe in this case also you need different structured materials, both MOFs and activated carbons. In both cases, the good thing is that you can play with the pore size. This is the critical property, let's say, of the material. So it's nice to hear from today that you can play with the conditions in such a way to regulate, let's say, the pore size more or less at will. It's a little bit more tricky with the MOFs, or more easy. Let's say you have more opportunities, but the synthesis is more difficult. But in all cases, both materials have a potential for these applications. Batteries, gas storage, gas separations as well, and carbon capture, let's say.
Yeah, thank you. Yeah, and all research is, if it's good research, will be useful at some point. So I think that's something that we have to keep in mind as well. So we have basically time for concluding remarks and finishing this workshop. So I'm going to ask each of you for just a final thought about either hydrogen storage, hydrogen deployment, or the carbon materials. So if you want, we can start with you, Theodore. If you give us one last thought about this technology or your project, what would it be?
Yes. Again, I have to thank you for this very nice workshop. So, in my opinion, as I said, we are in the start of a fascinating trip. It's good that we both got this problem, this project. Sorry, because it's a first step towards, let's say, exploiting this field in more practical terms than a simple scientific paper. So I have great hopes for the future, and hopefully at some point we can combine the materials, make something that will take the advantages of both worlds.
Absolutely, there's always a path for collaboration. Yeah, thank you very much, Theodore. Marta, one last thought about these materials.
Well, I think this is a good starting point, and that we can learn a lot from what we have already done in the project, and also about key challenges that we need to overcome in order to make the carbon materials have a real application in hydrogen storage or even in other applications.
Yeah, perfect.
Thank you again for hosting this. It's been very nice, very interesting. First time doing a roundtable. So. I guess I've got a couple of comments. It's been very, very interesting working with such a diverse set of backgrounds. I remember, like, what was the last General Assembly, or the one when we were at the factory and they actually had the vessel there, which I didn't actually. I mean, I think part of me was like, no, that's not going to actually exist. It seems like a long way off. One of the things or like a side project that I would like to come out of this, because it's a bottleneck in terms of our ability to design hydrogen storage materials, to design and test hydrogen storage materials, is some kind of new kind of high pressure, high throughput absorption apparatus, because at the moment what the project relies on, if the equipment is working, is me every day degassing and measuring an isotherm for a single sample. And Anna knows the pain of this, and actually Marta does too, because you were there. So, yeah, this, if to have any hope of like screening a large, you know, thousands of samples, we need much better capacity in hydrogen storage measurements, and I don't think the equipment exists for that.
No, yeah, good point.
Thank you, Scott. And for me, I've got a view outside from the project. It was very promising, the results from the amount of weight that it could take hydrogen compared with metal hydride, which is a commercial solution. It's probably smaller than when you use ammonia, which is 18% in weight. And I see that it's got still some work to do. On the TRL is low, so there are challenges, especially with the temperatures. I guess also with the alloys, the materials that you will need, that you require, especially the mechanical properties is also a challenge, and also the heat exchange for the process. And that's, but I saw the material itself is very promising with that 9%.
Yeah, thank you very much. I agree. I was writing down all the challenges, and I have way too many, so I'm not going to tell them. But obviously, there's been challenges. There are challenges for this technology in terms of the materials of the vessel, the design of the vessel, the heat exchange, this problem with the assortion being exothermic. And as well, we have challenges ahead of us for the assorting materials. Metal organic frameworks and activated carbon, not getting materials that work, that we could improve that, and ways of testing it that we can improve that, but as well the scaling up and getting to an economically feasible material that can be implemented in the future. So I think that we have many challenges, and this project has been, in our opinion, as coordinators, working really well, and we have advanced a lot. And we will be seeing the results hopefully in the following months when everything is put together. We are very excited about that. And with this, I would like to thank INCAR. I would like to thank Teresa for organizing a committee. Estivalita is here as well. And every one of you that are here, thank you very much for coming in person. The people that are online, thank you very much for attending the workshop. I hope that it's helpful and that everybody has learned something. At least I've learned something new, and that's good for a morning. And we will be making these materials available for anyone that wants to see the presentations. And thank you very much to everybody here in the panel, Tomás, Scott, Marta, Theodore, and Zakaria. Thank you very much for joining the roundtable, and